Oh, yeah, that's perfect. Thank you so much.
Oh, great.
That's a great help. Okay, cool. We can actually start now.
Sorry.
Okay. This microphone, is it on? Okay, cool. So make sure we use the mic. Okay, I think we can kick this off now. So
Es que no está hablando hacia el micrófono.
once our slides come on, we'll start our presentation. But I'm Nader Dabbit.
I'm Camila Ramos, and we're going to go through a presentation and then a live workshop. So, oh yeah, thank you. Part one will be kind of just following along, looking at the presentation. Then we'll break out our laptops, and you can follow along the workshop in real time. We also just published the repo and the slides and the code on Natter's Twitter, so you can go grab that now so you can follow along while Natter's working on it, or you can follow along later. Okay. Estamos esperando que suban los slides.
It seems it's connected good.
Yeah. Que ya estamos conectados, pero no vemos los slides acá arriba. Eso. Ok, perfecto. Great. Ok. Voy a manejar Spanglish porque estamos en Colombia. Yo soy colombiana, estoy muy feliz de estar aquí. Parte de mi misión como Developer Advocate, Developer Relations, es asegurarme que la educación sea accesible a gente de todas partes del mundo, yo específicamente en la región de Latinoamérica. I said I'm going to kind of maybe speak in Spanglish in some parts. One of my kind of core key mission statements as a developer advocate is to make sure that computer science education in general is widely accessible to people from all over the world. And that means that when you're in a different country with a different language, making sure that those people can access the education in the same way. I did a check here, and everyone here speaks English, so I'll lean more towards English on that for sure. And all of the stuff that's published is in English, but it would actually be great for us to potentially translate it. So cool, we're gonna do a Foundry workshop, a complete introduction to smart contract development with Foundry. So Nader is being my emotional support right now, but then we're gonna switch, then he's gonna get on and I'll be his emotional support. Cool, so Foundry is a portable, fast, and modular toolkit for Ethereum application development. So you might have heard of it, but you might have heard of others that fall into the same category in that part of the stack. So maybe Hard Hat, maybe Truffle. So it falls into the same place. It does the same thing where it's tooling around development. And we'll talk about exactly what are some of the unique values and the unique propositions that Foundry has and how you can leverage it in your smart contract development. So why Foundry? Like I said, there's other competitors. If you look here, there's, oh, is it ugly for you guys too? Yeah. Okay, it's okay. It's in the middle. So there's Hard Hat, there's Truffle, there's Brownie, there's Anchor. But kind of like, what is the unique proposition of Foundry, and why are we here talking about Foundry specifically? So a few different reasons. One is that it lets you write your tests in Solidity instead of JavaScript. And we say instead of JavaScript because I think at least for both of us, before Foundry, we were using Hard Hat. And when you're writing your tests there, you're writing your tests in JavaScript, even though your smart contracts are in Solidity. So with Foundry, it allows you to kind of have just less context switching and less mental overhead of like writing in one language and then testing in a different. The next one is that it's really, really fast. If you've used Hard Hat or anything else and then you use Foundry, you'll be able to feel the difference and tell the difference. And it's partially because it's written in Rust, so it's able to leverage a lot of the key properties that come with Rust and why Rust is gaining so much popularity right now. Another really cool thing that we're going to go over today in the workshop is an improved developer experience with fuzzing. So fuzzing is an automated testing strategy that basically lets you as a developer make sure that you're testing for all possible cases. So you know when you write unit tests or maybe functional tests, you're checking that an output for a very specific input matches what you expect. So you're like, check that the output equals 1, check that the output equals 2. But there's no way that you can manually write tests to handle every possible outcome. So that's exactly what fuzzing does, is it makes sure that you as a developer are seeing all of the edge cases, all of the kind of failed cases that are out there, so you can make sure that you're handling those. And then, so, ooh. Okay, one of these are out of order. So talking about the tools that come with Foundry, and what we're going to talk about exactly today are Anvil, Forge, and Cast. So starting with Anvil, Anvil's a local Ethereum node, similar to what you've already seen in Hardhat or Ganache, where you can spin up your local Ethereum node and use it for testing your contracts and interacting over RPC. Cast is another CLI tool that allows you to interact with the smart contracts. This is where you actually like send transactions, read data from the network, and we're not going to talk too deeply about this next part, but I would encourage you guys to check it out in the Foundry book, which is linked at the end. Cast also has some really cool subcommands that you can use for decoding call data and sending arbitrary messages and a bunch of other things. And then this is the one that was in the wrong place.
Cast. Or maybe not.
Oh, Forge. Okay, well, I didn't put one in the slides, but the other one is Forge, and that's like what you use to, like your tooling, what do you call
Yeah,
it?
it's kind of one of the main commands that you're going to be using on the CLI to generate a project and run tests and stuff.
Yeah, like when you do Hardhat in it, it's the equivalent to that, so when you're doing Forge. So now we're going to actually walk through. If you want to pull out your laptop, you can follow along. If you want to do this later on your own and just watch, you can do that. If you want to follow along, go to Natter's Twitter. He just tweeted out the link to it, so you can see it up close, so you don't have to squint.
Thank you for that introduction. So,
I'm going to get off stage and help people if they run into stuff while we're doing it, yeah?
So what we're going to be going over today is an open source GitHub repo that you can obviously follow along with today, or if you are watching at home or watching this at any other time and you don't have time to follow along, you can do this obviously at another time. But I've kind of tried to make this the most concise introductory level workshop to kind of get all of, to me, the most important, exciting things about Foundry covered in a short amount of time. And along with this workshop, I've linked to a couple of really great resources. One of them is the Foundry book, and it's a great resource, obviously. The other two, though, are one of them is something that I actually reference almost on a daily basis when I'm writing smart contracts with Foundry. And this is something I created called the Foundry cheat sheet. And this basically just has like all of the copy and paste commands for like the 90% of the work that I do with Foundry. So you might want to know, oh, how do you send a contract call to an address that's local? How do you send a contract call to a live contract? How do you do this or that? There's a lot of good copy and paste code that you can use here. And I believe that we are going to actually merge this into the Foundry book. There's already kind of a GitHub issue open there. So for right now, the Foundry cheat sheet is separate, but it might be part of the book later. And then the other is a video tutorial that I've done on getting started with Foundry. It's very similar to this workshop, but maybe a little bit more in depth. So with that being said, the only prerequisite for this workshop is that you have Rust installed. And if you want to see where this actual GitHub repo is, it's actually github.com/dabbit3. I think the URL was actually the slides there. So github.com/dabbit3, the very top workshop should be there. And the things that we're going to be covering today are testing and assertions, fuzzing, logging, running a local node, and deploying to that node. We're going to be looking at calling contract calls directly from your command line to that local node, installing and using libraries. So in Hardhat, we can use NPM to install like OpenZeppelin contracts and stuff like that. And with Forge, you can actually do the same. We're going to look at how to configure the remapping so that your text editor understands where these libraries are, but also the development environment knows where those are as well. And we're going to also look at some of the more interesting things that you're going to probably doing on a day-to-day basis, like mocking users. So let's say you want to kind of like run a contract call from one user and then test it out by transferring a token to another user and all that stuff. How do you do that? Well, we're going to cover that today. And that should be, I think, a really great overview. Once you go through this, then I think, at least for me, this was everything I needed to get started building. So with that being said, Cami kind of gave an introduction around a lot of this overview stuff that I'm going to skip now. And we're going to actually go directly to getting the installation done. Now, if you don't have Rust installed, it might take a little time for you to actually do that, so you might not be able to follow along. But once you have Rust installed, you're going to be installing Foundry up. And once you have Foundry up installed, you can just run this command Foundry up. And this will either install Foundry or it will install the latest version of Foundry. So before this workshop, I ran Foundry up and broke everything in the workshop because things changed. So I had to go back and make some updates. But the only thing that really changed with the new update was the actual original contract that was scaffolded by Foundry. They used to just scaffold out an empty contract. Now they scaffold out a counter example, which is actually much nicer. And honestly, it's also a good contract to play around with if you're learning. So with that being said, what we want to do is install Foundry by running this command and running Foundry up, like I mentioned. And what that's actually going to do, it's going to install a couple of different libraries or a couple of different tools, I would say. And Cami already kind of covered those. But once you do the installation, you're going to have 3 different CLI commands available to you. One is Forge, one is Cast, and one is Anvil. Forge we're going to use to create a new project. We're going to use it to do testing and stuff like that. Cast is actually what you're going to use to then make contract calls against any live contract. And it doesn't have to be a contract created by Foundry, actually. You can literally just use this Cast to interact with any live EVM network, which is cool. And then Anvil is what you'll use to spin up a local node. So with that being said, we're going to run forge init, and this will scaffold out a new project. So I'm going to go ahead and open my command line. And is that readable for everyone? Okay, cool. Try to make it big enough. So we're going to run forge init. Well, first of all, let me just show you that we're in an empty directory now. So forge init will scaffold out a new project. And while that's scaffolding out, I'm going to open that up in my text editor. And we're going to look at the folder structure. And we're going to see that we have the SRC directory, which holds our main contracts. We have our tests, which holds what? Our tests, obviously. And then we have our script, which is actually what you're going to use to deploy your contracts. And scripting is actually really cool, and I think it's something that wasn't there when Foundry first came out. And then lib is like the node modules, but it's for this environment. So if you install OpenZeppelin contracts, it'll go in the lib folder. And you can immediately start doing things. So if you wanted to run a build, you could say forge build. And this is going to compile your contracts, and it's going to give you the ABIs. So if you ever use Hardhat, you compile, you get your ABIs, and you can use those to make client-side calls, or you can use them to deploy and verify your contract on something like Etherscan. Once you run forge build, you're going to have this out directory, and this out directory holds your ABIs. You can also run forge test, and we're going to be actually running back through these commands again with a new code base because we don't really know what that's testing because we haven't even looked at the contract. So what I'm going to do is go back to my code base. And what I want to do is we're going to, instead of using this counter example, we're going to do a hello world, which is going to just give us a little bit more room to work with to show some of the functionality that you might not be able to do with just a counter example. So in order to do that, I'm going to rename this to hello world.sol. And everything that I'm doing is actually covered in the workshop materials, copy and paste directly from here. So don't worry if you're not keeping up. You can literally just go here and copy and paste. So what I've done is I've renamed counter to hello world. And this is a very basic hello world contract that I'm going to go ahead and paste here. The only functionality that we have is that we have 2 variables. We have a greeting and we have a version. When we make a new greeting, we're going to increment the version, and we're going to have a function that just returns the greeting. So it's about as simple as you can get, but it also, I think, is a good basic starting point, So the contract is there. This isn't on Solidity development. It's on Foundry development. So we're going to actually go now to the test, and we're going to spend more time on testing. And what we want to do is we're going to go to test folder /counter.t.sol. We're going to rename that to hello world.t.sol. And you're going to notice that in this example contract here, that we have a couple of functions, and they start with the word test. Now with Foundry, any function that starts with the word test will automatically be tested when you run forge test. It doesn't even have to be in this directory. So keep that in mind when you're writing your test. If you create a test in the test that doesn't start with test, it won't actually get tested, at least by default. So what we want to do is just go ahead and copy this test. Oops. And we're going to walk through the assertions that are being had there. All right. So we have this, the first thing that you might notice that's different is that we have this setup function, and this just allows you to create some type of initial variable or whatever that you want to reuse across all of your other tests. So it often makes sense to just create a new instance of the contract, and then you can just like reuse that instance of the contract. So that's kind of what we're doing here. We're creating this variable called hello that initializes a new hello world contract, and then we can just now say hello dot whatever the method of that contract is that we want to call. So the first test that we're going to run is we want to get the value that's returned from the greeting and make sure that it's what we expect. What we expect it to be is this, because the constructor takes in that initial argument, and we're doing that. Now that's interesting, but I think the most interesting thing to be keeping an eye out for is this assertion, assert equals. So you have about a dozen different assertions that you can work with. And I have a link in the workshop to all those assertions. So you can assert equality, you can assert things like greater than, less than, equal to, you can assert truthiness, pretty much anything that you would probably need for assertion. So it's a really, really basic test here, right? We're just kind of like making sure the greeting isn't equal to the string that we expect it to be. And then we're gonna also do an update, and we're gonna say the initial version of the version is 0, I guess you could say. We're gonna then create a new greeting, which should increment that version number to 1, and then we're gonna assert that that is equal to 1, and also assert that the greeting is equal to hello world. So with that being said, we can now run forge test. That should work. That's cool and all, but that's not all that interesting. Let's kind of look at more interesting stuff. So now that we have our basic project set up, let's dive into more stuff. So I mentioned some of these other assertions. We're not going to really be using any of those other ones, but here are some of them, and here's the link to view more. But what we want to look at now is fuzzing. So fuzzing is cool because we don't actually have to pass in the argument that is expected here. Fuzzing can actually take care of that for us. And therefore, you have also more, I would say, variation in the types of tests that are run, because it will basically automatically inject just different variables there. So instead of passing in the variable ourselves, we're going to use fuzzing here, and we're just going to define that there is a variable that should be passed in there, and then Foundry will automatically inject that, and it'll make it available for us. Everything else kind of, I would say, stays the same. So now if we run forge test again, it should still work. But if I go to maybe change this greeting to something else, obviously, like hello world, then that should maybe break. Okay? So the greeting that's coming in is some value that we don't know. So how do we know, what if we want to know that value? Well, we can start logging it out. And if you want to log, you have about a dozen different logging methods that you can use. You can just use a straight up basic log, which is just log, which is really simple. And you can also log integers, if you know for sure that it's going to be an integer. Log string, you can do log name string, which would be something like console.log, passing in the first argument as the string, the second argument is the value. So let's do some logging. So I'm going to go back to test 2, and what I want to log out is the value that is returned from the greet method, which should just be hello world. But you're going to notice when I run this test that nothing is logged out, because by default logging isn't enabled. You have to actually ask for more verbose logging. So what we're going to do is just pass the -VV, and then now we see that we have the logs there, so hello world. So that's how logging works. You just want to pass in the verbosity, and I think there's up to 4 Vs, and I don't know what that would do, but let's see. There we go. So I've never really needed that much, honestly, but okay. So we have some basic stuff going on. We're going to dive even deeper to more interesting stuff. We only have 5 minutes, but I think we have enough time. Next, we want to go ahead and run a local Ethereum node. So in Hard Hat, we would run npx hard hat node. In Foundry, you just type in the word anvil, and this spins up a node. And here you see that we have 10 different accounts and 10 different private keys. So what I want to do now is go ahead and set an environment variable to one of these private keys, and then that way we can start interacting with the network and referencing that private key as an environment variable. So to deploy the actual contract to the network, we need to run a script. And we already have a basic script in our project here under scripts. We want to just rename this to hello world.s.sol. And we have this run function, and then we have this broadcast method on the VM that actually does the deployment. And that's kind of where we're going to be doing our work. So I'm going to copy this, and not a whole lot has changed. We still have this empty setup method because we're not really using it. We're doing the VM.broadcast, and then after that, whatever is called will be actually deployed. And all we're saying is like, we want a new hello world contract deployed, and then we're passing in the constructor argument of the string, and then from there, we should be ready to go. So how do you actually run this? Well, we are going to use the Forge CLI, and we're going to say Forge script. We're going to define the location of the script. We're going to define where the RPC is that it's going to be deployed to. So if this was like in Fura, you would set an RPC endpoint. But since we're running locally, we're going to set the localhost 8545. And then we're going to set the private key as the private key that we stored in our environment variable. And then we're going to say broadcast, because if you don't say broadcast, it doesn't actually deploy that. So let's do this without broadcast. And I'm going to go ahead and open my terminal. And this will basically just give you a simulation of the deployment. So this will just tell you, whatever information about the deployment, like how much gas would be used and stuff like that. And then when you're ready to deploy, you just run that again. And then you just say -- broadcast. And then what you should be given is the contract address, and we're going to also be using that. So now we've deployed, and we see some logging that's happened there in our Anvil. And you also see the transaction ID and the contract ID. So now that we've deployed our contract, what we want to do is store that in an environment variable. So I'm going to go ahead and do that. Well, let me just do this. So we have 2 environment variables now. We have our contract address and our private key. And now we want to call that contract because we want to start reading information from our contract locally. So what we can do is say cast call, and we're going to pass in the contract address and the method. So we have that stored in our environment variable, so we can just reference it. And then what we want to do is call greet, and we know that it's going to return a string, and we get hello from Foundry. That's what we expected. Pretty basic stuff, but it's pretty cool to be calling that from the command line. We want to now send an update to update the greeting. So we're going to say cast send. We're going to say update greeting. We're going to pass in the new greeting, and then everything else is the same. So if I copy that, and then I go back and read the greeting again, this should now have my new greeting. And there we go. We've read the contract, we've updated, and we've then read the new value. So now that we've kind of gone over some of the basics, let's look at how to install a new package. So one of the most popular packages is Open Zeppelin contracts. So let's create an ERC 721, And what we want to do is just say forge install OpenZeppelin / Open Zeppelin contracts, very similar to like npm install. And what I need to do first is make a commit, because they don't like that if you have uncommitted code. Okay. So we're installing Open Zeppelin contracts, and after that's installed, it should just show up in our lib folder right there. And we now need to configure our remappings, because we need to tell our local environment where to find that code once we try to import it and use it. So you can actually run forge remappings and see already whatever remappings are configured. And here you kind of already see them trying to kind of make some assumptions about your environment. But we want to set a custom remapping. So if you would like to do that, you can actually just create a new file called remappings.txt. And we will set our remapping for Open Zeppelin here. And now we can actually just import that directly from Open Zeppelin without having to reference the entire path. And it looks something like that. So we have maybe 3 more minutes, and we're already over a little bit, but we still have just one more thing to cover. We want to look at mocking another user, which is, I think one of the more useful things that you could probably like learn here. So to do that, we're going to be going to make a new ERC721.sol. This is a really basic contract, but you see now we're actually importing from Open Zeppelin contracts, which is pretty cool. We're creating an ERC721 called Devcon Panda, and we will just have a mint function, pretty basic stuff. And we're going to also have a test for this, because this is going to be the part where we're actually learning something in the test. Okay, so the test that we have set up for right now is really basic. We haven't added any of the mocking features yet, but what we want to do is simulate another user. So we have 2 users, we have Noah and we have Sophia, and what we want to do is like create a token, transfer it to another person. We want to make sure that only the owner of that token can actually transfer the token. So to do that, we are going to use the prank method. And you can either say prank, and prank will be using the next call only to prank that user, or you can say start prank, and we'll do all of the users, or all of the calls that come after that until you call stop prank. So this will like wrap up the workshop. I know we're a little bit over. I'm going to go ahead and create the function that we're going to be doing here. And we have this method where we're going to test a transfer. So we want to mint a new token to Noah. We want to start pranking and simulating us being Noah. We want to then transfer to Sophia, and then we want to check the owner of that token and then assert that Sophia is indeed the owner. And if we run forge tests, that should work. We want to actually only test this contract, and if you would like to do that, you can pass in the match contract. So now we're only testing that one, and to make sure that everything is working good, we're going to assert that Bob is the owner when he's not the owner, and everything fails, which is what we want. Okay, so that's basically it. We're not covering everything. You can run forge coverage, which is a pretty cool command to give you test coverage. And you can go even, it's not working because the test has failed. But anyways, forge coverage is really nice. So that wraps up the workshop. I'm sorry we started a couple minutes late. I'm sorry we went a couple minutes late over. Check out the GitHub repo. Walk through all that stuff a little bit slower if you'd like to learn more. Thank you.
Is this your phone?
Yeah.
So I wanted to know if I could pull gas reporter also on the
the gas reporter. I thought you said ticket.
No.
Okay, yeah. You have, there's gas reports and all kinds of stuff.
All right, Miranda, can you hear me? Test. Can you hear, anybody hear me? I can. Let's see if I go into presentation mode how this goes.
The resolution should change right away. Then.
Yeah.
it
So,
did.
so
Okay.
and do I want to go into presenter mode? Is that what I want to do?
Do you need the notes at the bottom?
I mean, if I can look at them, sure.
Yeah. So. Okay. So. Okay. Yeah, that should be good, right?
Yeah, I think so.
Sweet. Yeah. We'll see in a sec once it turns on. If not,
And then do I need the audio jack?
if you have audio playing, is there going to be any
It's
audio?
gonna- it's gonna-
oh, it's her. Yeah.
It's
sorry.
her. Yes.
Yeah.
I thought he had it a second ago. Oh, yeah. It's a good time.
Audio or HDMI audio? Because we could also just do. Sorry, I'm going to exit this. Auxiliary? Okay. Can we just test out YouTube to see if it works?
Sure. Or no, Miranda, you want to say something?
Maybe they need to turn up the audio on their end.
We already have it. Maybe you need to set.
Oh wait, let me change the sound device then.
Yeah.
Okay, you can hear the ping.
Yep,
Yeah, okay, so that should be good.
we can hear you. Okay. We just didn't hear. We didn't hear when they talked.
Can we try?
Miranda, say something again.
Hello.
Yep. Okay, perfect.
Did you hear that?
Yep.
Yep.
Perfect. Okay. Do you have the slides down there? Can you see my slides? Yeah? Good? All right, cool. All right. Hi, everyone. Andrew Foreman. I'm with Ernst & Young, EY Blockchain. I'm here talking about Starlight. So basically, so I work at EY. I work with a lot of our clients that are building smart contract applications, any kind of Web3 app, new governance features, things like that. What I'm not is I'm not a cryptographer. I've never taken a cryptography class. I don't really understand the math behind zero-knowledge proof circuits. I know there's a couple out there. So what Starlight is really just a huge leap forward in allowing any average Solidity developer, myself included, to start to bring and use privacy features in the construction of their dApp and their smart contract. So this is very much like a, if I can do it, you can do it too kind of talk. We do have some of the cryptographers that worked on building the application on the phone, and they'll talk through some of the technical parts of it. But definitely want to give you a feel for what this is, what we're building here. Maybe just another important note too is that this is something that we're actively working on at EY. It's pre-alpha release. Very much an experimental technology, so like we're hoping to launch it soon. But and the reason we're talking about it this weekend is so that you guys can see it, you can start to use it, give us feedback, and then we can have a more robust launch very shortly. So what is Starlight? So like I said, the big headline here is that any Solidity developer can now use the power of zero-knowledge proofs in building private features for their dApp on-chain. You don't need to understand kind of all of the sophisticated circuits, the elliptical curves, anything like that, to go then build private features for your dApp. So that's what Starlight was built to do. It's really two things. It's one, it's a zero knowledge proof library for writing your Solidity code, and two, a transpiler. We call it compiler, but really it's a transpiler to then read that that library file and the decorators that are involved there. So what you can do is then you take any of these decorators do is they take any of your variables, mappings, arrays that you have in your contract, and it allows you to put them into a private state. And so then what kind of some of the names you see up here are kind of the names that we've been using. I mean, these are kind of like right now just internal names that we're trying to experiment with. But like when you take your dApp and you run it through this this kind of construction that we have around decorators, we're calling that a ZAP, or a zero knowledge proof app. The Solidity is the file type that we use in this zero knowledge proof library, which is in the Starlight library, which I'll get to in a bit. And then Zapify is really just the command to run the compiler. So like once you understand kind of some basics around those decorators, it's really just 3 steps. Write your Solidity, add these decorators, run the compiler. And as you can see, like we've taken all of that, trusted setup, circuit construction, trust assumptions, logic off of you as a developer. So all you have to do is add this to your Solidity code and kind of understand what the logic is going to look like for your users and how these state changes get updated. Okay. So first one, we said 2 things, right? First is the compiler. So I think I want to say, like, why did you even build a compiler? It's kind of like a weird thing to even go and tackle. You don't see it that often where someone wants to go build a compiler. And so for us, this was really just about scale and getting more developers access to this technology. It was something that I ran into personally on a project. So we worked with a client. They wanted to build this private donation platform. And what it allowed you to do was take a bunch of different charities, make private donations to them. So now like a large donor who may not want their donation to be public could do so privately on chain. So there's like a big step forward in like more sophisticated, more real world smart contract applications. But I worked with like a team of advanced cryptographers. We had to go through weeks of circuit construction. They had to explain it to me so that our team could then write it into Solidity code. All of that stuff is not scalable when you talk about hundreds and thousands of zero knowledge proof based and privacy enabled applications. So to make that all work, we started kind of at the compiler level so that you can keep writing your Solidity code, add these decorators, and run it through this construction. So the 3 steps, again, we'll say take your contract in Solidity.sol, add decorators, you mark what you want to be secret, variables, arrays, mappings, anything that can have a private state. Then send it through Zapify into our what we're calling this compiler, transpiler. So then, how does that look at runtime? Because it's kind of this is like maybe just like also as like a developer education point. Understanding what's happening to your code as you go in through and deploy it. So what we have here is the compiler takes that Solidity code, and we have this ZOL file, this Solidity file type. And what we're going to do is we're going to first kind of make sure that the syntax and the way your Solidity code is written looks right. That there's no Solidity errors first. We're going to run it through the Solidity compiler, just like as your code always would be executed. Then we're going to add back into this AST tree, which we've broken out, the decorators that you put into that file, and then we're going to run it through our transpiler. And so now we've gone through this compiler loop a second time, and what you have is a Solidity or a ZAP that's been compiled. And so that's when we would then set up and create the circuits and the state changes that you would need for that application. So yeah, that's kind of what it looks like at the back end. You're going to have one tree that has these 3 different parts, which is the shield contract, this orchestration code, and then also just your basic your Solidity file structure. And I only call that out now because when we get into the more technical parts of the talk, you're going to see that breakout again of the orchestration, the shield contract, and the Solidity file. Okay, so like I said, all that you need to know as a developer is how to use these decorators and how to run it through this transpiler, and you've got your Solidity app ready to go. So I want to now jump into the decorators because this is really kind of like the key thing for anybody that wants to go and use Starlight to understand are these three decorators. Miranda, can you hear me, or do you want me to take these ones? You want to try and test talking and see if we can hear you? Hello? All right, well, I'll get started. So the first one is the secret decorator. So what secret is like, think about any kind of like variable, whether you declare it at the global level or a function parameter that you want to remain in a secret or private state. So like your basic example here, and we can jump to the code as well, is I've got variable A. I don't want anybody else to be able to call and see what I have stored at variable A. So I can put a secret in front of that argument, and now it can remain private on chain. Known and unknown. So this is getting a little bit more advanced. So then think about this as like a bank account, right? So a known would be where I know what's in my bank account. I can now update the state of my bank account, and so I would use known for that if I want to add or decrease. If I don't know the state of my bank account, so let's say I want to change his bank account, I don't know what's in his bank account, I would use unknown, and now I can add to his bank account without knowing the state of it. So that's how you would use known and unknown. It really, a lot of this comes down to kind of the language of ZKP and privacy and cryptography is just like who's creating the commitment, who knows the secret word at any point, and who can update the state of that whether it's a variable, mapping, or an array. And so to me, this is just like a very nice distillation of a lot of zero-knowledge proof work happening in the background, where for me, all I have to understand is how to use these decorators, what they're going to look like once my code is represented on chain, and now I can start to kind of bring these features of zero-knowledge proof and privacy into my application. Who can change states? Who knows things when, and who can update them? So let's look into an example of that. Miranda, if you can hear us, you can jump in on this one as well. You start talking.
Can you hear me?
Maybe it's a little loud. You want to try that again?
Hello, can you hear me?
Yes, we hear you fine. Perfect.
Yes, we do. Okay, perfect. So we're going from the example, is that right?
Correct.
I can't see the slide, sorry. Okay, great. So you have an example here. So if we want to Zapify something and turn it into a zero-knowledge application, we start with a smart contract, as Andrew talked through. So let's do this super simple idea, which hopefully has some kind of use case. We have a mapping of invoices from an address of a person to the amount in the invoice. We have the owner of the contract, this is the one who's going to be paying the invoices, and we have a function to add invoices and a function to pay them. So you see in red, these are where the decorators are. So we don't actually need to worry about known and unknown here because we're overwriting state and we're decrementing state. So we know that essentially the only people who are going to call these functions are the people who know and own the state. And the compiler's clever enough to work that out for you. So we don't need known or unknown here. But yeah, so this is an example of a kind of input you would be able to put into Starlight and Zapify. At the bottom is just a very high overview of the actual application. by compiling this, we would get a shield contract which would verify the information you put on chain. In this example, we are not revealing any owners or amounts of these invoices, so very little information will go on chain apart from the proofs, the proving you've done these computations correctly, and the amounts based on whether you're adding a new amount or whether you're decrementing some amount. The orchestration is just the node code and a bunch of other types of sort of deployment type things, so like Docker, NPM files that help you deploy and use and bring together the zero knowledge and the on-chain parts, and the Socrates files. So Socrates is the code that we use for our zero knowledge circuits. All right, so on the next slide, there should be a sort of example flow of this example.
Yep.
Yep, so lovely. So ideally here, so the user wants to add an invoice using their zero knowledge application that they've made with Starlight. So number one is the only step that the user has to do. All the rest is done in the background, and the user's just waiting for the receipt back from the transaction. So they want to privately add an invoice to this contract. They still need to input an amount. So if you remember in the previous slide, we still need the user to input an amount, but then the rest is done in the background. So they call, instead of calling the contract, they would call a JavaScript node file. And what that would do, if you have an old invoice for this exact owner for you, then it would grab that old commitment. If not, it would use a dummy commitment, which is a bit of an advanced feature, but we'll just continue. It would get all these inputs together and create all the things that we need to keep the state private. So in this case, in number 3, we want to wrap the amount into a commitment. So what we do is we hash it with lots of other information as well to make sure that it's hidden, but it's provably correct. And we go through exactly the same computations that we did in the original input contract, but instead we do it in the zero knowledge circuit, and we prove that we've done it correctly rather than revealing the inputs that we've used. And then once we've done all this, in number 4, we send this proof, the new commitments we have, so the new commitment representing the new value, and the nullifier of an old commitment if it exists. We send that on chain. If the contract that we made, if that verifies the proof, it adds a new commitment to a tree, so you can prove that it exists later. It basically tells the world, but mostly our Merkle tree application, that a new commitment has been added, and it adds a nullifier so that you can't double spend any commitments. So all the user had to do was step 1, and the Starlight generated application has done all the rest. So the user has added a completely secret invoice to this application. Yeah, that goes through the example.
Yeah, great. I'm just trying to see if I can switch over to the actual repo itself. I don't know if we can do that. I mean, here's another example just to bring it up again. I mean, I think that was a good example that Miranda walked through, and I think maybe just like some other examples to throw at you just to get you thinking about how you would use these decorators. Might be something like if I wanted to have a voting contract and I wanted to restrict the number of people that could vote in that contract, but I wanted to keep those 10 people private, I could create a mapping that says, here are my 10 voters, they're private, and so you can go and check on chain. You wouldn't be able to see who's allowed to vote in my contract, and then maybe only I or some admin has special privileges to change the voters on my in my application. We've thought about some other ones like issuing IOUs or different kinds of like advanced commitments. So I think this one's like an invoice example. I think that like these are powerful tools, and now we can start to think about what are the privacy features of our users. When do they want their information to be private, or some other part of the application to be private? And then this becomes a way that we actually instantiate that feature. I'll flip over to it in a second, but we have a GitHub repo that is public, and anybody can go and access it. I'll put up a slide after this, and there'll be a link there to get to it. There's a lot of good examples there, a lot of good test files for you to go through. So we definitely want people to go and try out the repos, take a look at it, see if it makes sense. If you have questions, we're available to talk through any parts of it that you want. And then maybe just to hit on two kind of learnings that we've had over the last few months working on this repo. One, building the compiler is really hard. Like it's hard to find compiler developers to work on this. There's a lot of different test cases that you need to be working for. I wouldn't advise it for your health to go work on compiler code. It's a mess. So, if anybody's a compiler dev, come find me. I'll get, recruiting dinner. And then I think too, for me, the big opportunity and the big thing that's changing in our space and as for Ethereum developers, EVM developers is building privacy into our applications. And I think as these applications become more sophisticated, as they start to have more real world applicability and use cases, as our governance systems get more sophisticated, that we're going to want to have privacy in the things that we put on chain for our users. And it's not feasible right now at this point just assume that everybody's going to go out and understand how a snark works at a very detailed level to go build those applications. So I really think we need tools like this to be able to make the privacy features that we want and that'll make the space better work. And so I think something that'll be a big focus for myself and our team going forward too is just helping designers, developers, product managers think through what are the feature designs they want to build in and how do they start to think about privacy in a more robust way. That's pretty much all on the talk. Can I switch over to the GitHub? I'll just show you guys where it's at. Here's a link if you want to scan it here. And you just heard from Miranda. She was one of the lead developers. Michael Connor down there in the stands also worked on it. Swati Rayal is part of our R&D and cryptography team in London. And Megan and I are kind of helping as developer relations, so to speak. All right, I don't think we're going to get the GitHub. But yeah, come find me after the talk and we can walk through the repo. Okay, thanks everyone.
Hi there, guys. So I saw some of you at the booth already. Today I'm going to talk about how Cartesi is bringing Linux to the blockchain. And I'm going to explain how that's possible. And I'm going to show you a Python example of how that works. So this is a quick overview of what we are going to do over here. So I'm going to talk a little bit about Cartesi, what it is, how long we've been around. And I'm going to do a light comparison between Web3, Web2, and Cartesi development. And then I'm going to actually talk about Cartesi rollups. I'm going to introduce you to rollups for those who are not familiar with it. And then I'm going to go dive into the code. However, I want to keep you hooked. This is the code we are going to investigate together. So this 27-line Python code that's actually importing libraries from normal Python. It's actually running on a virtual machine that can act as a rollup for Ethereum, for instance. This is actually a smart contract. This one here is doing an echo Python. So whatever you send it back on the blockchain for you. So Cartesi. Cartesi is a company that was founded in 2018. These guys have been working a long time trying to bring a RISC-V. I'm going to talk about RISC-V, but a processor, a true processor to the blockchain, how to make it deterministic so you can do like normal computations. And that's why they're calling it the blockchain OS, because we actually brought the Linux for it. So the overall idea, I guess you're all familiar with it, so I'm just going to run through it, is that Ethereum is awesome, it's secure, it's somewhat censorship resistant, decentralized. There's all these good features about Ethereum. However, it becomes slow, it is expensive, so dApps are actually fighting for space, resource inside of the blocks to actually be processed. And it comes with a lot of friction for developers that are just coming to blockchain. So you have 30 years of experience, doesn't matter, you're gonna start all over again, you know? So the idea is, what if we can do complex computations and maintain the main layers security guarantees? So here's the Cartesi response to that. First, we use a transparent VM. So you are able to actually see the whole code. It's not somewhat complicated, but it's open source. Like the last guy was saying, compiler stuff is hard. But in any case, it's open to everybody to investigate it. And it is using the RISC-V, like I said. So RISC-V is an open hardware platform, just like open source, but for hardware. And it comes with a lot of security guarantees already, because it's being audited by several companies and people. It has been updated. It keeps getting updated throughout the time, so that's nice. Any person is allowed to build on top of it. And it is a platform processor, which means you can actually have any kind of OS on it. It's a very robust machine. And the only thing that we need to actually adapt is to build a deterministic emulator. So we made RISC-V deterministic. And because of that, we could actually make the emulator for EVM as well. So whenever you run the computation off-chain, it is possible to actually run the same computation on Ethereum right now. In fact, one of our acceptance tests is to actually do the whole RISC-V acceptance test on-chain. So of course, it's a testnet, or a local testnet, but we do it on the EVM just to prove that the version that we have on-chain is the same exact version that we've developed in C++. So that allows you to have massive computation on as a layer 2. And with that, you develop the whole way this works. The idea of to actually have the massive computation not become yet another limiter, again, is to have a local consensus. I guess people here are more familiar with app-centric rollups. So because of that, instead of having a lot of computation, doing the same work over and over again, effectively only having a single machine, which is the way the Ethereum works, you can actually have computational resources dedicated to each application. So every application is its own rollup if you use the Cortese framework. Finally, the most important thing is to actually make it work with the blockchain, right? So that's where the dispute protocol comes in. It's not any novelty. It's actually been discussed for a long time. So here we are using the verification game. The overall idea is you get the whole computation you did off-chain. Let's say it took like 3,000 cycles, CPU cycles. You find exactly where the validators diverge, and you only have to execute a single CPU instruction cycle on Ethereum, which makes validating the whole process really cheap. So the, the end result is Ethereum becomes a judge. So it means that if you have, I don't know, like 4 people playing a poker game, and one of them win, and the other 3 start to collude against the one that won, that single honest validator, that's all that you need, a single honest validator to come to Ethereum and complain about the end result. And then Ethereum is gonna judge who's telling the truth. So you guarantee the correct settlement of computation. So for those who are not familiar with rollups, the overall idea is you have the main chain, it has its own blocks. At some point, you initiate the process. You tell Ethereum, here's the initial state of my rollup. And you go on with your life for a little while off-chain doing computations. And once you're done, or once you want to do a checkpoint, because that's the idea of rollup, you always checkpointing your process. You go back to the blockchain. And with optimistic rollups, you actually have like a 7-day window for now, like that's the agreed good time span for disputes. So you have a 7-day window to actually complain about anything that went wrong on that block of computation, so to speak. So how it comes, how everything gets together, right? So before, in Web 2, you used to have like some kind of a front end, a few APIs defined by you to be run in a centralized server or a set of centralized servers talking to a set of centralized databases, right? That's the main Web 2 idea. So Ethereum comes up and say, you know what, like the business logic, whatever is most important, you can actually decentralize that. So you figure out a way to deploy your front end. You can use IPFS, which is really nice, and you communicate with the blockchain. Cortese doesn't change that too much. The overall idea is still you have the same feel as the Ethereum. You are supposed to have a set of nodes that you communicate with, just like what happens with Ethereum, to have your backend be the base of your app. The main difference is instead of burdening the developer with all the little things needed to actually communicate back to Ethereum, we developed this, we are calling here HTTP dispatcher. It's just an API that encapsulates all the complexities of communicating with the blockchain back. So basically what you need is just to communicate with a REST API. So there is a definition of that. There's 3 endpoints. You get to learn how the endpoints work, and now you can develop your your smart contract in any language. That's the overall idea, and I'm gonna show that in Python. So how it actually looks like. We have the 3 main pieces of APIs. The first one is the JSON RPC, it's just there. So that one is still like Ethereum. So you have a data availability issue, right? You are settling on process, like on computational disputes, but it's still egg and chicken situation if you don't have an agreement what was the inputs that you had for that process. So the idea, yes, let's keep using Ethereum or any other layer 1 networks to just communicate what were, I don't know, our chess moves, for instance. So you have the JSON RPC there still to do inputs to the rollups. However, you have the graphical API that we developed. And the graphical API is mostly so you can check on 3 things that we have on the Cartesian machine. So over here, we have report and notice. They are similar, but different enough. So report is any kind of log that you log within the Cartesian machine. Think of it as a developer debug log. So it's not provable, it's ephemeral. You cannot do much with that. It's just to help you out while you're checking the health of a process or you're developing your dApp. However, the notice is our version of Ethereum events with a twist. So right now, if a ERC20 token says there was a transfer between an A and B party of some amount, it's trustworthy enough if you're running the Ethereum node. However, you have no proof that the event actually exists. You have to be running the node to trust the event. The notice, however, comes with its own proof. So the notice is part of the machine state. So if you go back to Ethereum and you have to, and you create other dApps and interact with other dApps inside Ethereum or even on other optimistic rollups, you can build upon the idea of having notices. So let's say you have a transfer happening inside the Ethereum machine. It doesn't need to be a direct call. You just need to say, hey, I actually won the game. Let's say an NFT generating situation. So in order to win this badge, like the winner, like you have to prove that you won 10 times the game. You just collect the 10 notice and you can put it to be proven on Ethereum, for instance. So that's how it is different from an event. And voucher, the final one, is basically a Ethereum transaction that is yet to be. So whenever your rollup dApp wants to communicate back to a smart contract in Solidity, for instance, it creates a voucher. And if the optimistic rollup settles and there is no disputes on that, after the 7-day window, the voucher becomes executable. So it becomes actually an Ethereum transaction. So you as a user could just call it and claim the voucher, or you could let the validators on the network do it for you. There is like fees and other stuff going on that. So that's why you have the graphical API, because if you want to populate your front end with that kind of information, you can access it directly calling the node. Finally, we have an HTTP REST API that works like ETH call for those who are familiar with Ethereum. Basically, it's any call that you do to the machine that is not state transitioning. So we ensure that this call, we always roll back to the initial state of the machine. That's the main difference. And that call only can generate reports, because that's what I said before, right? It's something that it's not provable. So the idea is to have quick dApp communication. You can use it to grab data for your UI, and you can use it as a debugging solution as well. It's easier to check up on the state of your machine, of your program. So now I go back to the Python example. So to this yellow side over here, we have a tool on our rollup examples repository, but basically they're encapsulating JavaScript code, like how to actually call stuff through the JSON RPC, right? Just it's a helper tool. And over the blue side, I have the actual Python dApp. So we're going to start sending like a payload with just hello there. That it is just a transaction call data, nothing special about it. And we're going to start checking what happens on the code. So from the beginning, you can see that I can use all the support that Python offers me. And I'm going to start using requests because I want to talk to the API that I just talked about, right? I want to be able to do HTTP requests. I grab from the environment where is the actual URL for the HTTP API within the machine. So we provide you with that environment variable for you so you can actually just grab it without hard coding it on your code. And here we have the two types of handlers I was just talking about, but from the API's perspective. Within the machine, here are the two types. If you receive an inspect state kind of a request, it means that the whole machine, the whole emulator, will revert back. Oh, something happened. Okay, now we're back. So it will revert back to the previous state before the request. However, if it is an advanced state, it's basically telling you, this is going to change the state, so you should do it properly, basically. With that, it's just the high level. You can subscribe and create as many endpoints as you wish. It's just like Solidity in a sense. At the Solidity code, you basically have the entry point, and you do all the switch for the functions, right? Here you have the main loop. So the idea is that this machine halts. It doesn't stop. It just halts. So every time you finish a request, processing the request, it just halts at the end, and it wakes up at the next input. So this finish over here is actually a kind of like a next. So it's actually saying, hey, I'm ready. Wake me up whenever you have something. So you stop over here. So as we begin for the first time with the code, you're going to see that I have like finish status accept. And that's what I'm sending to the emulator beneath it. And it's going to halt. And then when I say hello there, it's going to wake up the code exactly at this line. And from here on out, we are just going to process this request. So I send an input, so it should be an advanced state kind of request. So we're going to just pick up the JSON data from there, actually go to the handler that is responsible for that. So that's the advanced state. And add a function. At this time, I'm just going to create a notice, just the notice with the same data I just received. So I grab the data payload and put it in the notice payload back. It's just a simple program in this case. And I'm going to call the API creating a notice. That's what that's doing. It's not going to halt the machine. It's just saying, hey, here's something that it is an output from this process. And I can call it as many times as I wish. OK. And the result is accept again. It's all fine. So I'm just going to jump over the inspect for a second. So I would just add to the status, accept. And because I am in a loop, I'm going to end up here, the finish again, sending the accept status, halting the whole machine. However, if I had the handler of the type inspect, meaning instead of sending an input over there, I would actually try to inspect the machine, saying hello there. You would go to this different handler. You would create just a report, just like the notice is not that different when you see the code. And it's the same. I just finish. And whenever I ask for the helper to list all the new notices that there is there, you're going to see that the machine would return you with the hello there as a payload. And that's the overall idea. Do you guys have questions? I guess it's too much. Yes? Oh, yes. So, yeah, it's still a blockchain environment. So, in a sense, you're not connected to the internet. You can have internet at the Cortese machine when you're first building it. So, remember the rollups example thing I was doing, like initial state? So, let's say you're building your machine, building all the dApp, and you need data. So, I don't know, Docker images and NPM installs and things. You can have that, for sure. But once you're in the rollup environment, you don't have that access anymore. Make sense? So, go ahead.
What's the cost of deployment?
So there is the cost of deployment of the rollups itself, like the set of smart contracts and stuff. It's not that high. I don't actually have a right figure for you right now, but it should be something around feel like $50 or something for Ethereum right now. But just so you have all the insertion points, so to speak, on Ethereum. Because this dApp actually has a mirror address on Ethereum, so other dApps can communicate it, through it back to the Cortese rollups. But in terms of actual cost of running this thing, it's up to the dApp developer. You say, do you want to charge people for using it? Do you want to just you and other developers run the nodes? Do you want to incentivize your users to run the nodes? It's up to you. In the sense, Cortese is more like a framework, really, because it's really app-specific. You tell the parameters. You don't like the 7 days because you're doing a simple game, like if really simple, low stakes, maybe it's just 5 hours for your rollup settlement window. Make sense? You had a question?
Yeah, so is the expectation that everyone is going to be running their own infrastructure, like they are setting up the machine that is going to be running this VM?
I mean, it's up to the dApp developer. If it is something that makes sense, I guess, sure. But yeah, right now we're in the middle, right? We understand that mostly we're still going to have like the service providers running the nodes and people kind of like trusting them. Yeah. Any more questions? Okay. Thank you.
Should I wait until 17:30? Okay, I think we can start. Can everybody hear me? Yeah. In this workshop, we will take a look at how the graph provides critical infrastructure to Web3, and you will then learn how you can create your own API that is tailored to your data requirements. My name is Örjan Övesta. You can find me on Twitter, Web3 SlimChance. You can find me in Discord, SlimChance 1699. I'm in the ETH Global Discord if you need any help with any technical questions. And you can also find me upstairs. We are right by the elevator, so drop by our booth if you need any help with your subgraphs. So let me first start with the question that everybody asks me. Why do we need index data? The blockchain is public, right? But most blockchains are optimized for writing data and not for reading it. And you can imagine the blockchain as a big public library where every day there comes a new truckload of books, and these are not sorted in any way. They're just added to the end of the shelves. And imagine that you go into this library and you want a list of the books with the highest word count. If you were to do that using a traditional like RPC or just connecting to a blockchain RPC, you will need to check every single book, note down the word count, and then create your list. And this is where the graph comes in, as it allows you to index this data beforehand. Let's take a more practical example. A DeFi dashboard. Most of you are familiar with Uniswap, a decentralized protocol for swapping tokens. Some of you might also know that there's a dashboard called info.uniswap.org where you can get valuable charts and data about the protocol. Now, if you were to retrieve this data directly from an RPC, you would need to do a call for every single time there's a trade, the price would change, so you would need to check the price. And to get a chart like this, you would need to do millions of calls, which would be very resource heavy, really expensive. So that's why we need to pre-process this data. It would also take you an enormous amount of time because you would need to process this in the front end. So again, index data allows you to have this data in real time in your application. All of the data that you see on info.uniswap.org is provided by the graph. So you might think, who needs the index data? And we found out that that is everyone. We are currently seeing over 64,000 subgraphs have been created on the hosted service, and over 640 billion queries have been served by the graph. So why are people using the graph? Well, you can create a customized API that is tailored to your data requirements. This includes rich, sorted, filtered, and aggregated data. And it allows for fully decentralized and serverless applications. If your dApp relies on a single centralized server, it's just an app. The graph currently has two services. The hosted service, which is a centralized service run by EdgeNode, one of the core developer teams at the graph. It supports 38 different networks, NEAR, Polygon, BNB, and 35 more. We are currently moving to the decentralized network, where we currently support Ethereum mainnet, but we believe every dApp deserves decentralized open APIs to retrieve their data from the blockchain. And we are delivering on that with the current ongoing MIPS program, where we are incentivizing indexers to start indexing other blockchains as well. And that is a historic step forward, not just for the graph, but for the entire Web3 ecosystem that relies on us and wants us to provide them truly decentralized open APIs. And to dive deeper into why do we need decentralization in the infrastructure layer? Well, there's no central point of failure. You never have to call your backend engineer at Sunday morning saying that your server went down. It is naturally load balanced. The graph is infinitely scalable, and it does so seamlessly. It is geo-distributed service. We currently have indexers on every continent with over 200 indexers that are currently on the graph network. You will never wake up to an email from your service provider saying that your server went down because your service provider have taken a no crypto stance. And most of all, well, this number is a little bit outdated now. We now have 220 indexers, all competing to deliver the highest quality of service to the lowest possible price. And this is why I am excited about the graph, and I hope also you guys will be excited to use the graph this weekend and going forward. So I'm going to stop there, and I'm going to ask if you have any questions about the protocol. If not, we can move on to the next part. I'll dive into the subgraph. Yeah? And thank you. So it's not incentivized for indexers to split their stake over multiple nodes unless they're also running the service in multiple geo-distributed locations, which at that point, well, let them, because they are just also providing better service to the network. Yeah. So let's dive into, I've touched a little bit on what a subgraph is. It has three major parts. The subgraph manifest. Here you define your network, the contracts you want to, or the network you want to index, the contracts on that network, the start block, because when you get that blueprint to the indexer, they will start indexing the data from a certain start block. It can be from the Genesis block or from any other block that you specify. And what events, calls, or other triggers to listen for on these contracts. The subgraph schema is where you define the data structure that you want to query. And this is where you want to think ahead and make it as close as possible to the data requirements of your application. You would have the data structure, the entities, relations between the entities, and so on. Then, where you will spend the most time as a subgraph developer is in the mapping code. Here you map data from the events that you have specified and to the data structure that you also have specified here. And you would also do any kind of transformation, aggregation of data will happen in the manifest or in the mappings. But that is written in assembly script, which is very similar to TypeScript if you work with that. So let's dive into it. Let's look at how we can create a subgraph in a very short amount of time. So this is the graph. In the graph, you have access to what's called a subgraph studio, where you can log in with your MetaMask. I'm already logged in and created a few subgraphs on other workshops. If I wanted to create a new one, I click Create a Subgraph. I want to create one for mainnet. In our case, we want to index, in this workshop, I will show you how to index the BASI contract, so the Bored Ape Yacht Club. Let's call it ETHBogotá, for example. So now you have created this in the subgraph studio. In the subgraph studio, you can see some important information, like it is currently undeployed. It is having a subgraph slug, which is the identifier you will use in some of the CLI commands. And you also have a deployment key that you use to identify yourself, so only you can deploy changes and upgrades to this subgraph. What you would do is you would first install the graph CLI. I've already done it on my machine. Then you will initialize your subgraph. Let me duplicate my screen so it's easier. Now, a cheat code that I like to use is the index events flag. This will create a scaffold code where it's indexing all the events that it finds in a certain contract. It asks us which network or which protocol type that the contract is on. It's an Ethereum contract. the subgraph slug, the directory, and then which networks it on, and it's on mainnet. Now the contract address, I'll save that. Maybe I'm not connected to the internet. Let me try again. There you go. So now it's creating a subgraph scaffold for us with scaffold code. Just give it a second. It's a tough time to download things from the internet here, I believe. Maybe if everybody turns off their phones and their laptops. So there we go. Now we can add more contracts. I just wrote no here. So now we have a subgraph in CD Bogotá. So here we can see the three files that I talked about earlier. You have the subgraph YAML, which defines what to index. And in our case, we are looking at the BASIC contract and on mainnet. At this address, I will add a start block as well, because we don't want to wait around for it to index all the way from the Genesis block. So I'm adding that. Here. We have the schema. It is currently pretty sparse. It's a simple indexing of all the 4 events on this contract, approval for all, ownership transferred and transfer. And then in the source file, you have the mapping file, where you see all of these entities are being stored. And this has already been created just by using the index event flag, and I recommend using that as a way to populate your code with some boilerplate events and entities. Now we are ready to deploy. We can do graph code gen. This. Now, if you go back to the studio, you can see that you would also authenticate your laptop first or your computer first. I've already done that, so I can go all the way ahead and do graph deploy. Give it a So now it's uploading all the subgraph files to IPFS so that indexers can fetch that data and start using the subgraph as a blueprint to then transform raw blockchain data into the open API that is a subgraph. But in our case, we are just deploying to the studio, which is a centralized service, and it's a place to stage and test your subgraphs before deploying it to the decentralized network. So it's deployed. Let's check it out. Let's refresh the page. And the subgraph is already fully synced, already fully populated with data about every single event that has happened on the BASE contract. So this is pretty cool, but what really we can do with subgraphs is then go back in and add aggregated data. Say you want to find out, okay, how many Bored Apes have been traded every month, or how, what is the total value of, or like, what other aggregated data you want to have in your subgraph. You can add that then to the mapping code and then redeploy. So, for example, we can go into the schema and say that we want to simply, like now we have all the transfer events, but we don't know when they happen. So we could, for example, have a timestamp. And then in the, then to create that, to create the timestamp in the, so you can access it from the mapping code. You would run graph codegen again. Now it's created the types for us, so we can access them in the in the mapping code. So now I could go in on the handle transfer and save this in entity dot. You see now it's appearing here. Timestamp. Event dot timestamp. So now if I were to redeploy, that's all that is needed to add that to your subgraph code, and thus you can reiterate and add more functionality to your subgraph. Is there any questions so far about writing your subgraph? Yeah. Yeah, so the question here is if you are using upgradable contracts, and in this case, you can use something that is called like dynamic data sources, which is a way to then like change or add more data sources while the subgraph is in production. And that is used for example, upgradable contracts. Another use case is factory contracts, like say, for example, Uniswap. Every time a new pair is created, you want to create a new data source, which is the new pool. And in that case, you would also use dynamic data sources. It's also called templates somewhere in the documentation. So it would be templates in the manifest, for example. But yeah, I can give you some documentation after this talk if you want to dive deeper into it. Questions about subgraphs or creating a subgraph? Yeah. So
the graph QL Studio generates that URL, and we just point
that is correct. And I will show you now how to query subgraphs. And I won't show you the front-end code, but I will show you how you can create a GraphQL query, and then you can use it depending on like how your front-end like what language you're using in the front-end application. You can then use that query. So. If we go back to the graph.com, as I mentioned earlier, we have a graph explorer or if you have a decentralized network, you can find subgraphs that is on the decentralized network via the graph explorer. We also have the hosted service, which has 30,000 open APIs that you can query. I will show you how to query one of them. So let's, for example, say we want to query the synthetics subgraph, for example. Here you can create a GraphQL query to test your query. Oh, it's not a valid query. This is you can save your queries and use them. Let me instead open the endpoint. This takes us to a GraphQL Explorer that allows you to create your own GraphQL queries using a simple like checkbox type of interface. So you can, for example, find like the synth holders, order by synth, and you say you want to have the first 10. And now if the internet is with us, we can get a query response. So there you have the first 10 synth holders ordered by synth. And you can, with our prizes here on the hackathon, we have 2 tracks. One is creating a new subgraph, so a new open APIs, as I showed you 10 minutes ago. And the other track is using an existing subgraph in your application. And here you see it is very, very easy to create a query, and the power of using GraphQL is that you can get exactly what you need. So no more than that, and no less than that as well. You don't need to have this reiteration that you often have to do with SQL, where you have to first maybe find the ID of something, and then you need to go back in and find the fields that you are looking for. But here you can get everything in one query. Yeah.
What determines like the speed the subgraph is indexed?
So what determines the speed of that a subgraph is indexed? That's a good question. It depends a lot on how you write your mapping code. So there are some patterns that you want to avoid when you're writing a subgraph. For example, you want to avoid doing an excessive amount of ETH calls. So in a subgraph, you can do ETH calls at a block and get the state of the chain at that block, and you want to avoid having an excessive amount. So you don't want to, for example, create a loop where you are looping through a lot of entities, and for each of them doing a query to an RPC endpoint. So you can do that in a subgraph, but you want to limit that. So each query takes around 100 to 200 milliseconds at a rule of thumb. So a few of them doesn't matter, but if you are doing 1,000 of these and you're doing that every block or every event, every transaction, it's going to be costly when you are indexing a subgraph. Yeah. Yeah, so the question was querying a pass block or pass range, and you can unless you have like deleted an entity in the subgraph, you can just find it directly here. Like synth holders this will also hold all the synth holders since this started indexing. But there's also a feature called time travel queries that queries the state of a subgraph at any block that you specify. So say that I want all synth holders at a given block. I can get that using time travel queries. So here you would have block number, and then you would write, for example, a block number here. So at this state, this subgraph started indexing at block 5 million and change. So I cannot query block 2333. So, but any number that I put in that is over this 5 million. Does everybody see my screen, by the way? Is it? Yeah. So at that, yeah, cool. And, yeah.
What did you mean by cheap? I mean, every query block, when do you pay that?
Yeah, so again, we need to differentiate between the decentralized network, where you're paying for queries, and the hosted service, which is completely free. You will pay for query costs. So first of all, like with the subgraph that we just created, it's currently on the subgraph studio, which is the staging area, and that is also free to use. Once you deploy your subgraph to the mainnet, so let me see the ETHBogotá here. This is the one I just created. This has a development and query URL that you can find here. That is completely free to use. You can also use the playground to play around with it. But once you want to go into production and use this subgraph or to use this API, you would go to publish, and you would publish it on mainnet. And at that point, you will also need a API key to query that subgraph, and you will pay query fees in GRT. Yeah. I'm done. So yeah, we can take that afterwards.
All right, guys, thank you for joining. I'll get started in just a second. All good, all good. Just give me 1 minute here. If you're looking for superfluid, you're in the right place. All right, so we will get going then. Thanks to everybody who is here. It's fun to be in Bogota. I think all the LATAM events that I've been to have been great so far. The communities here are excellent. But yeah, no, I'm excited to get started and talk you guys through Superfluid and also show you some examples of how to actually get started with Superfluid with code, right? So let's go through building on Superfluid at ETHBogotá. So what is Superfluid, for those of you that don't know? Well, it is a protocol that enables something we like to call real-time finance, right? So the one big way this manifests itself is through something called money streaming, right? So Superfluid enables these money streams, which are digital native programmable cash flows that let you stream money with no capital lockups in a way that is 100% programmable and on-chain. So at Superfluid, we like to say that the internet is to information what blockchain is to value. Right? We believe that we're in the very early innings here of new forms of finance that will bring this old world of finance into the age of the internet, right? And one way this manifests itself is through the way that payments work for things that have to do with time, right? So services, right? So if you think about services businesses, right? If you're an employee, you're kind of in the services business as well. With services, the way that these work is that they flow in real time from a provider to a client, right? Netflix is something you watch in real time. Your work is something you provide in real time. However, the issue is that the payments for that value are disconnected from the way they're actually being provided, right? So you work through an entire month and you get paid at the end of the month, right? Why shouldn't you be getting paid every second? So let's dive into money streaming a little bit more, right? This thing you're seeing there in the bottom right-hand corner of the screen is a live money stream, right? That's ETH being streamed on a testnet. And you can think of these as continuous payments, right? We are used to a world of discrete payments. What if we could make them continuous, right? What if we could create this direct link between the service provision and the value transfer in return for that service? And the other thing that's cool about this, because it's all on-chain, it completely gets rid of any delays, unpayment risk, or any intermediaries because it's all mediated through blockchains and smart contracts. So how is money streaming possible? Well, we built an EVM-compatible smart contract framework to make this happen, right? And it's made up of 3 pieces, right? So we'll get into how the heck this thing here is happening in the bottom right-hand corner, but it takes some building up to it, right? So these 3 pieces are Superfluid agreements, super tokens, and the Superfluid host contract, which brings everything together. So what are agreements? Well, these agreements are peer-to-peer financial relationships that are open-ended and perpetual between 2 accounts, right? Or potentially more than 2 accounts, right? When I create an agreement to stream you money, what's happening is I send a transaction on chain, which agrees to stream you a certain number of tokens per second. And that amount of tokens that I'm streaming you per second is actually built directly into the token balance. So we'll get into how the token balances work in just a moment, but what's happening here is within the constant flow agreement, right, which is the main agreement that facilitates all this money streaming, you define that flow rate and money begins flowing immediately in real time from you to the receiver, right? The sender or receiver can be smart contracts, right? It doesn't matter, right? You're just executing a transaction and money begins flowing in real time. So literally this right here, these simple lines of code, CFA v1.createFlow receiver token flow rate will open this money stream, right? It will create this. In the end, as a developer, it's quite simple, but to understand how it works, we've got to go a little deeper, right? So this is all great, right? You might understand this concept of an agreement. Yeah, I kind of get that, but how are you doing this without calling transfer like every millisecond? How is that not how this is working? And the way we get around this is by building an extension onto the ERC20 standard, right? So we built an extension onto the ERC20 that comes with all the stuff you're used to, approve, transfer from, symbol, all this stuff. But the way balances are calculated will take into consideration all of the agreements you have outstanding for any given token, right? So within that balance of function on a super token contract, there's another call that's made to something called, to a function titled real-time balance of, which takes into consideration your real-time balance, right? And your real-time balance is really just an aggregation of all of the money being streamed to you and all the money you're streaming out to give you a kind of single net flow rate. So let's dive into these a little bit more, right? Again, ERC20 compatible, plugged into the protocol, and what's cool about it is they're usable anywhere in Web3, right? So we know that interoperability is like super important within this industry. So for existing ERC20s or even native assets like ETH, AVAX, Matic, or other native assets and other chains, we've built wrappers, right? So you can go wrap USDC. Like actually right now, my salary is paid using a wrapped version of USDC called USDCX. If you see the X appended to the end of a symbol, it just means that it's a super token, right? It's a wrapped version of that existing asset that enables all of the streaming functionality, right? It's a wrapper super token. There's also native super tokens whose supply is 100% streamable. So if you know about Superfluid, you learn about Superfluid today, and you decide to launch a token, you might opt to just deploy it out of the box with all these features so you don't have to wrap anything. That's an option too. There are several of those out in the wild that have a lot of usage, so that's another option. But the key thing to keep in mind is this real-time balance, right? It's an aggregation of all the incoming flows and outgoing flows to create this kind of single number the protocol needs to keep track of to figure out how many tokens you should be sending or receiving every second. If anybody else has any questions on that, I will stand out there right outside the door and answer as many questions as you guys have, just to make sure we really drill that into your heads, because I know it can be kind of weird at first, but it is critical to understand if you're gonna interact with Superfluid. Okay, the final thing here that's important for understanding how the protocol works is this thing called the Superfluid host. The Superfluid host brings this all together. It's like the brain of the protocol, right? So it's made up of some whitelisted agreements. Again, the main one is that constant flow agreement, which defines how balances can be changed using that constant flow formula. It also is something you call when you deploy a super token. It supports something called batch calls, which lets you just batch a bunch of Superfluid-related operations into a single transaction, which is kind of helpful. You can do things like open 150 streams in one transaction, other crazy stuff like that. And then it also serves as a registry for something called a super app, right? So what is a super app and why is that interesting? Well, the other interesting component of Superfluid is that it is programmable, right? You can build contracts that are aware of these streams coming in, that have callbacks, which can automatically run whenever a contract starts receiving tokens, whenever those streams are updated, or whenever those streams are deleted, right? So this opens up all kinds of really interesting connections between smart contracts that forms a really interesting network that I'll show you a visualization of in just a second. But to understand these, you have to keep in mind that all of these callbacks here, this after agreement created thing you see in the bottom right, these are called by the Superfluid host contract, because when you deploy a super app, you just register it with that host contract, which is the brain of the protocol, right? So that the host contract will know, hey, this contract that is a super app is receiving tokens, call this function with your arbitrary logic in it to do something else cool, right? So again, there's lots of super apps deployed right now, and they all kind of do different things. One big one is called Ricochet Exchange, which allows people to stream funds into a contract and effectively dollar cost average into different assets, right? So right now I can go DCA from USDC to ETH on Polygon, and all that's happening in real time, right? So it's just like this loop where you have a contract that's receiving funds and sending funds out. And what this looks like when you start stitching things like Ricochet and these other contracts together is this, right? You get this really crazy network of cash flows where every single green ball there is an account, whether it's a smart contract or an EOA, and all the connections between them are cash flows, right? So for you here that are considering building applications on Superfluid, you have a gigantic network of cash flows to make use of, right? Point them into new places, build new things for them to do, and we'll try to reward you for it. So a quick little aside on the prizes. We have 10K in prizes this weekend, 3K for the best overall project built on Superfluid, a few $2,000 prizes for various purposes like DeFi and best use of superfluid and NFTs. And then we have this thing we call the pool of honor, which is just a pool prize, where if you implement superfluid in some capacity, we'll throw you some money. Just don't do things that I've seen where some of you guys just throw a little git commit there at the end and just add a couple lines. I'll actually look, all right? But just wanted to plug those. But all right, let's get into actual building, okay? What do you need to know about before you start actually building on Superfluid? Well, you should be made aware of a couple of dev tools, right? The first is the Superfluid Developer Console, right? This makes it really easy to see all these streams. Etherscan is not quite optimized for this sort of thing yet, as you can imagine. So we built our own console, right? It makes it easy to manage all this stuff. We have a dashboard that lets you create streams and update streams and all this stuff in a no-code way, if that's your thing. And we have an SDK. Right? So if you like JavaScript, you like TypeScript, you don't know Solidity, the SDK core is your friend. Right? And I'll show you how to use that in just a second. So let's build, okay? And I guess you know what, before we click away, I'll go over what we're gonna build. The first thing we're gonna do is we're just gonna interact with some really dead simple front-end examples. So this is for you React fans out there, you TypeScript, JavaScript fans out there. We'll go to our docs, I'll show you where to find these. We'll create flows, update them using JavaScript, all right? From there, we'll actually go through the process of building a super app in a couple of minutes. I got a pre-deployed contract here that will receive incoming streams and send all those incoming streams to the owner of the contract. And plot twist, the contract is also an NFT, right? So if you trade this contract, the cash flow follows it, right? So it's a really interesting primitive to let you tokenize cash flows, which can open up a lot of really interesting applications in my opinion. So, first thing I'm going to do is go into our docs, where we have a lot of front-end examples. All right, so let me expand this a little bit here. All right, so in our docs, you guys can, if you have computers out, you can literally go to this right now, docs.superfluid.finance, and in developers, if you go to constant flow agreement, it just says CFA front-end examples. Super easy to find. To create a flow, what we do is we import the Superfluid SDK over here. You can kind of drag this over and see it. Sometimes on bad internet, these don't load great. All right, we might find an alternative to code sandbox, but this is what we got for now. But we just set up a simple React app, and we have a really dead simple function here where we initialize the SDK using this line, where we create this framework object, we specify the chain ID. You can get this dynamically, but I just hard-coded it squarely. We create a signer. We load the super token contract using this diex.load, or not diex, this await sf.load super token line. So that'll load a super token contract object for us. And then we'll create a flow. So what we do is we just create a really simple operation object using sf.cfav1.createFlow. Pass in a few parameters like the flow rate, receiver, and super token. And then we execute that from our signer, okay? This is hooked up here. It's hooked up to an exposed private key, right? You don't have to have an unlocked private key to do this. Obviously, that's not the preferred way for you to do it. It's just really easy because we have an address with a ton of fake tokens in it, and we let you just basically demo this in real time. So here I have an address I pasted in. I've got an amount here, which is our flow rate. This thing down here will calculate what that flow rate actually is, right? When you put this number in, this is actually in wave per second, right? So it's helpful to have a kind of formula for UX purposes to calculate what this actually is on a per month basis. So what I'll do is I'll just click this to create the stream. This should work in just a second. All right, so we just created a money stream. So what I'm going to do is I'm going to plug this address into the console. This is the console. Check it out. Useful tool. If you click home, you can see a bunch of streams, right, on different networks. If I want to click on Guerli, I can just paste in the address that I just used to send the stream to. And we can see that we are receiving some money, right? So I just created a stream to this address. Pretty cool, right? Not very much has come in yet. That's because it's a pretty small amount, right? So we created a stream. In this, in this page, we have a few other ways you can do this, right? So we have at the very bottom a MetaMask and Web3 provider example where you can just use MetaMask. Yes, question.
Sorry to interrupt, but for the address that's tied to this
So no, one thing I'll walk through what I think you mean. If you're starting with a DAI and you want to stream money with that DAI, you have to wrap that DAI to super token DAI, right? So again, if you want simple examples of that, again, we got more front-end examples here around, let's go to tokens. Super tokens, right? We'll walk you through how this works. And then we have an example here that's just like the other interactive ones, where you can just call the upgrade function to wrap those tokens, right? That's the only thing you have to do. But if you already have those wrapped DAI in your account, no. You just call that function and boom, you're good. Make sense? Cool. All right, so I won't belabor the point, right? You can imagine that updating and deleting is very, very similar, right? I won't go into those, but that is dead simple, creating, updating, and deleting streams in JavaScript, right? Pretty straightforward. Really easy to integrate with any other project you're probably working on. For a more complex example, let's get into this tradable cash flow thing, right? This super app thing. And I have a project up here. I'll show you where to find this after I'm done. We have this in our main repo. I'll zoom way in. Hopefully you guys can see that, all right? But inside of our examples, this is inside of our super examples repo. We have this tradable cash flow example here, okay? So this is gonna look exactly the same as it does here, as it will in that repo. We have two contracts. And the first one is called this redirect all contract. So what the redirect all contract is it's a super app, which means that it allows us to send money into it. And then when we send money into it, we can execute arbitrary logic in these callbacks to do something, right? That something could be anything you want. But in our case, what we're going to do is we're just going to send 100% of the value coming into the contract to the owner. All right, so we have a bunch of stuff set up in the constructor. Right, we initialized this CFA library to make it really easy to create streams in Solidity. I won't go too deeply into that right now, but the cliff notes is it makes it so that creating a stream in Solidity looks a lot like how it did in JavaScript. We register the app, right? So remember that that host contract has a registry of super apps on it. So we need to register it. And we need to define the callbacks we do and don't want to use, right? We have docs on this that explain this in much more detail. But in essence, there are 6 callbacks that can run, right? There's a before agreement created, an after agreement created, before agreement updated, after agreement updated, and the same for deleted. The before will run before the actual logic takes place. The after will run after the event takes place, okay? So we're basically just turning all of the before agreement options into no ops. We're not gonna use them, right? So the only callbacks we're gonna use are these after agreement callbacks, okay? So inside of these, right, we get a bunch of parameters that the host will call it with. And we're going to run a single operation here, and that's this update flow operation. What's happening in update flow? Well, all we're doing is we're just checking whether or not a stream already exists into the contract, and we're handling that situation accordingly, right? So if there already is a stream coming into the contract, and the operation is a delete operation, that means we need to not only delete the stream coming into the contract, but also delete all the funds coming out of the contract, right? The 100% of the inflow should equal 100% of the outflow. So we're just basically making sure those match in this function, right? But again, the limits here are your creativity. You could put whatever you want here, right? This is just one example. The other function here that's useful is this change receiver function. This will run every time the token is transferred. So if I want to sell this NFT, this change receiver function will run, which will just change who is receiving the flow, right? So if I sell it, we'll take as a parameter here the new receiver, which is going to be the person I sold it to. That person's now going to receive 100% of the outflow, right? Simple enough. And then inside of this tradable cash flow contract, it's an NFT, it's an ERC 721. It inherits from the redirect all contract. And then we use this nice little helpful before token transfer hook that you guys can find in the Open Zeppelin API docs. And we just call that change receiver function in there. So I have a pre-deployed version of this. Let me go to it in just a second. And I got a bunch of scripts. So we're going to interact with it really fast before we wrap up. So I have some scripts. Let me grab this contract address so we can go look at it. This right here will be our tradable cash flow NFT address. Right? We can see I've been playing with it. I've been sending streams to it and stuff. But if I want to create a stream to this NFT contract using a script, what I can do is I can just call this create flow script. Right? And what this is doing is it's basically using the same logic we had in our React app. We're creating a flow with the script, right? So we're just doing this in Node instead of the React version we just saw a bit ago. So if I run this using hardhat, create flow.js, we're going to create a flow from our signer into the contract on Guerli. This should work. Please, internet gods. All right. Yep, I think that just worked. All right, in a couple of seconds, as soon as the transaction propagates and stuff, we'll go back and see what just happened inside that NFT contract. But again, if you want, we can go through the update examples, right? Instead of it being create, we're just calling update. And instead of, same thing, instead of create or update, we're calling delete here, right? The only difference in these functions is that the delete function doesn't need a flow rate, because there is no flow rate, we're just deleting. Okay, so let's refresh this. Again, prayers up to the internet gods, see if it works. There we go. All right, so what we can see, let me zoom way in. What we can see is my account just created a stream of about 33 tokens per day into the contract. Right, we can see how much has been streamed in, and we can see that because, again, 100% of the flow into the contract is going to go to the owner. So there's basically no net flow rate for this thing. It's just basically coming in and passing it all through to the owner. We also have an outflow rate that was automatically created. Right? We didn't create that. Those callback functions created that, so it reacted to that operation for the exact same amount, right? So that they match, right? And that's the idea. So that's end-to-end a super app contract and all of those JavaScript SDK examples, right? It should get you started and hopefully give you some ideas. To wrap things up here, I want to walk through like what else you could build, right? I have a lot of ideas, right? A lot of people here that are sponsoring will tell you they have lots of ideas that you can take and build on, but I'll just give you a few right now, right? One interesting one is a platform for token vesting. Our community would like to see this, right? Streaming money is good for vesting tokens, right? You do have to lock the funds up in a contract at first, right? But money is being sent per second, right? So it's pretty useful to be, as you're vesting, be able to vest on a per second basis and actually receive the money second by second. The other one is Web3 native subscriptions, right? So these are all recurring payments, right? They're money streams. There is no canonical yet. There are some great teams we love working on it, but there is no canonical Web3 native subscriptions platform that uses money streams yet. You could build that. Another one is a decentralized advertising protocol where you could effectively turn that NFT contract I just showed you into like a billboard space, right, for banner ads, and have all the money streamed into it be sent to the owner of the billboard, right? You can do interesting things in those callbacks, like split the funds too, if you want. Two other ones are around like lending, borrowing and lending. One of them is a lending protocol that you would use streams to amortize loans. So what if I could pay off a loan with a stream, right, instead of discrete amounts? Our hypothesis is that doing that would justify a lower interest rate because the lender is getting their money back faster. It's more granular. And the final one that's really interesting based on that huge network I showed you is being able to borrow against an incoming money stream, right? So there's a lot of people receiving salary streams right now, right? I'm one of them. There's many, many others. What if I could, because that's a cash flow. It's an on-chain cash flow. It's proof of payment. What if I could borrow against that, right, and not have to put up any other collateral? That would be really interesting, and it'd be the kind of thing that I personally would try out. Right? So there are markets here. These are things we've thought through a lot. If you guys want to build them, come up and say hi at our booth, and I'm happy to help. Finally, like what I want to leave you with is where to start. Okay, like if you leave here and you're curious about Superfluid, where do I go next? All right. Well, the first place is those SDK examples inside of our docs. Go to our docs, constant flow agreement, front end examples. The second place is our Solidity examples repo. Look up Superfluid Finance on GitHub and look for super examples. And I'd also recommend YouTube for a lot of tutorials, more in-depth stuff. And the last thing is a podcast we just launched, right? So this really doesn't have anything to do directly with Superfluid, but it is a great resource for technical people like yourself. We've interviewed a lot of top devs from Maker, Balancer, Uma, DevRel leaders like Austin Griffith about like very technical topics, right? Like their favorite gas optimizations, how they ship new features, how they manage their engineering teams, all this stuff. We try to pull it out and give you guys the insights. So I'd recommend checking it out. Devs, do something on your favorite podcast platform. But yeah, that's the last thing I'll plug. I'll leave you with that. Come say what's up at the booth, and thank you for being here. Appreciate it. All right. Thank you.
Mic test. All right, I think we're good to go. Hello, everyone. Thank you for coming. I'm Ulyss from AP Wine, one of the co-founders of AP Wine Finance. And today I'm going to be presenting this workshop in mainly 3 different points. What AP Wine is, how it works, and how you can integrate it into your own hackathon project in order to win some prizes. So we're going to begin with, what is AP Wine and why did we build it in the first place? It all started during the DeFi summer of 2020, where APYs were just crazy 3 digits. And we just saw the opportunity here because there was no way to bet on the loss on the rise of yield. So essentially reduce your risk. This is why we came up with a new primitive in DeFi called yield tokenization. And now yield tokenization is, mainly the core of AP Wine Finance. And this is what allows you to get your yield in advance or trade yield. So yield tokenization allows you to buy, sell, and hedge your risk in DeFi on your yield. Now, how does it work? It all begins with, if you use some funds on Aave or, Compound or any yield-generating platform, you have some interest-bearing assets. Interest-bearing assets is, you just hold your tokens and it increases in value or it just increases, yield in your wallet. So as an example, I've taken, ADAI, a pretty common asset to hold in your wallet. It just increases in value, and this is an interest-bearing token. Now, if you deposit that on AP Wine, this is the yield tokenization part. We're going to split it into 2 tokens. So one of them is going to be the principal token. And this represents the value of your deposit at the time when you deposit. So essentially, imagine you deposit 100 ADAI on AP Wine, you're going to get 100 PT, principal tokens. And these principal tokens are always going to represent 100 ADAI, right? It's always the same value. And now what's interesting is the future yield token, the second token that you get. And this is going to constantly, when the ADAI is generating yield, from AVE, it's going to put this yield not into the principal token, but into the future yield token. So essentially, we're splitting the capital and the future yield. And this is what allows us, to get this entire marketplace of future yield going on. So you can mint PT and FYT with your interest-bearing tokens, and you're never locked in the platform. You can always withdraw if you still have the PT and the FYT. And then we have the AP1 AMM, which is a core part of the protocol. And the AP1 AMM allows you to sell this FYT or buy PT or just trade between any of the three assets of ADI, PT, FYT in order to build your own strategies or get your yield in advance or fix your rate or so on. Our AP1 AMM is the result of many months of research. This is the AP1 AMM V1. We have impermanent loss protection mechanism for LPs, so if you want to become a liquidity provider on AP1, it's also very easy to do so, and maybe we can chat about it after the workshop. But in order to get straight into the workshop, I'm just going to mention a few strategies here, and then we're going to get into what we're going to build today. Some of the strategies you can build with AP1 include PT trading. So this is like equivalent to a fixed rate, essentially buying PT at a discount. Imagine if you're buying PT at 0.9, so 90% of what it's really worth. It means that if you wait till the end of the period, for example, 3 months, this is what we work with, you're going to make a 10% profit because you know for sure you're buying something that is going to be worth more in the future. And this is how you fix your rate. Now, without going into too many strategies, this is what we're going to be doing today. Today's workshop is about going back to the future to fix your rate on your yield. So we're going to be leveraging the yield tokenization part of AP1 plus the AP1 AMM in order to build this strategy. So some of the prerequisites, and if you have your computer, it's great. If you don't, you can just follow along, but it's also very easy to follow with the GitHub repo. So you need Yarn, Node.js, and we're going to be starting now with the repository setup. All right, is this one? All right, it's fine. I'll just keep like this. All right, this is going to be a one-handed workshop, which is going to be interesting. Let's go with the repository setup. I'm just going to get this a little bit higher, and we're going to git clone github.com/ulidev/ap1-workshop. And if we clone this repo and we navigate to it, let's open it in code to better see it. And you're going to be able to see everything that it contains. The first step you're going to want to do is copy the environment file into from the example file to your environment local file. So .f.example to .env. I've set up an API key for you to try. Please don't use it for anything else. It's not going to work. All right, and then we just want to install all the dependencies. So you just want to go with yarn. This is going to install all the packages, just like npm. And while we do this, let's take a look at how we are going to follow along. So first step we're going to do is yarn start node. This is going to start a node, a fork on mainnet. So essentially, we're going to be simulating our strategy without actually using money, which is very useful. Because if your strategy doesn't work, you likely just want to simulate it before. So if we do yarn start node, this is going to do a local blockchain fork. And then we want to open a new tab. And every time we want to follow along a step, you can just do yarn step 1, yarn step 2, all the way to 5. So just as an example, let's do yarn step 1. And then we can go look into the code to see what it does. So here we can see that it initializes the SDK, and this is the first step that we're going to take a look at it. So first step is the SDK creation. Very simple, just one-liner. This is going to be a JavaScript workshop, not a Solidity workshop. But if you're interested in integrating within Solidity our contracts, we can chat about it. It's also very easy to do so. First step, SDK is equal to new AP1 SDK. You want to put your provider, your signer, everything that you need. The network, which is going to be mainnet. And that's it. A new world opens to you, the world of future yield. So this is the first step that we just did. The SDK is now initialized and ready to work. Second step, so just to explain how this is going to work, what we're going to do is first see how we can do the very basic PT trading strategy. So buying PT for cheap and waiting till the end and seeing how much APR do we get. And the second step, which is the real workshop that we're going to do, is go through future yield. So essentially tokenizing into PT, FYT, and then swapping our future yield for fixed rate. And we're going to see that this is much more capital efficient. So hang on. This is the first step. How do we retrieve all the futures APY support, all the assets that we support, all the platforms and so on? What we can do is this. Futures is equal to sdk.fetch all future aggregates. Very simple. You get all the information that you need. Let's try out. And while we do this step, so this is going to actually run on the main network, we can take a look at what it does here. So if we go to scripts and then step 2, get all futures, we can see exactly what it does. So here, fetch future aggregate from address, and we just pat whatever future vault address we want. And if we go back here, we can see here the results of all the assets that we support at this time of the fork. This was a fork from a few months ago. We now support many assets around 2 chains and many different platforms. But here we have, for example, and this is going to be the one we are going to look at, we have staked ETH from Lido Finance. Anybody ever used a staked ETH before? Yeah, so you can generate APR, at 5%, 6%. Depends on, what you're getting, right? And this is a period that expired on the 23rd of March of 2022. So this is, an older fork, but the principle stays the same. You can try with a newer block number, and it's going to work just as well. And then the next step we want to do is compute the APR that we would get if we were to buy the PT for this specific staked ETH future. So how do we do this? We're going to use the AMM this time because we want a special price, right? If you want to buy or sell anything, you're going to have to go through the APY AMM. So price is equal to sdk.fetch spot price. You pass the vault, so this is going to be our staked ETH vault, and then from and to. These are 2 different strings. So you can put underlying, PT, or FYT. Very simple. And this is what we're going to do right now and see the results. So yarn, step 3. And we can take a look at what it does here, compute PT APR. So here the result is that we get an APR of 35%. Remember, this was before, how is that possible? The magic of DeFi. This was, very close to the launch of APY. So there were still, many opportunities available for arbitrage. There are still many opportunities available, but just keep in mind that this was an older date. So essentially at this time, you could get 35% by just buying PT. And this is a fixed rate. So you're guaranteed, hacks aside, that you're going to get your APR. So how do we do this? We just do compute APR. So this is a helper utility method that just, according to a price and an expiration date, you can compute how much percentage this is going to give you. So for example, if you're getting 1% on 1 month, it means you're getting 12% per year. Very simple. This is what it does. So we are getting a 35% APR. This is very, very good. But there's one detail. The spot price is never equal to what you're really getting. So if you were to buy $1 million worth of PT, you would have a lot of slippage because the liquidity at this time was much lower. So what we need to do is go through the other strategy, which is much more capital efficient. By capital efficient, I mean that you can have much bigger volume for the same exact APR, or very similar. So the efficiency that we get is good, but it can be better. With lower resources, so lower liquidity, we can get a same or better result. And this is what we're going to do in this new step. We're going to go through not only buying PT with our ETH, but directly staking on Lido Finance, so ETH, staked ETH, and then deposit that on APY. So it's going to go like this: ETH, staked ETH, and then tokenize into PT and FYT. So this is the step we're going to do right now. Let's do it. Yarn step 4. And we can take a look at what it does. So essentially, we're depositing, I made another utility function here, very simple, to deposit ETH on Lido Finance. So this is going to convert your ETH into staked ETH. And then we're going to deposit on our future vault here. And what you get at the end is, if you deposit 10 ETH on Lido Finance, you're getting 9.93 PT and 9.93 FYT. Why is that? Why don't I get exactly 10 PT and 10 FYT? The reason for this is that the future already started, a few days ago. So it already generated yield, right? So you need to account for this. But if you were to withdraw everything, you would get your exact 10 staked ETH back. This is because one FYT, in this case, already has some value. So if you add the value of your PT and the value of your future yield, it's going to be exactly 10 staked ETH. Nice. Now we're ready for the last step. We have our PT, our FYT, and what we want to do is go from FYT to PT, so maximize our fixed rate. There are also other strategies you can do. For example, you could do the other way around. You could just swap your PT for FYT, which means that swap your FYT for ETH, which means that you would get your yield in advance. Remember, FYT is the future yield token. If you swap it for ETH, it means essentially that you're selling your future yield for yield today, right? And this is where it gets super interesting because you can do so many strategies with it. So swapping FYT, let's do it. SDK.swapIn, provide the AMM entity, and then from FYT to PT, provide the amount. Very simple. It's going to do the routing automatically from FYT to PT and then ETH. So you don't need to care about it. Now let's look at the result. Yarn step 5, this is the last step, and then we can go with some questions. So if we do this, it's going to do a lot of computations and simulate everything on the blockchain. And final guaranteed APR with this strategy is 34%. Again, this was during the time. You can try again with a different block number, for example, today's block number, to see what you would get. And it could be interesting, to do so and simulate by your own. Or you can just try with real money. So this is what we get. The difference with this is that this is much more capital efficient. So lower slippage, bigger trades, up to 10 times, depending on the APR and the APY and the pool that you've selected, and the composability, because you can swap from any of PT, FYT, ETH. So it's very interesting to use the AMM in that matter. Right, so we just basically with a few lines of code, just 5 very simple steps. If you put it all in one file, it's going to be even simpler, but I've kind of split it to make it easier. But all of this to say that in a few lines, you can have your fixed rate APR with a very simple strategy on APY. So if your project, if you're still looking for ideas, we could brainstorm together. But if there is anything from arbitrage, trading bots, leveraging of yield, or just there's even some people there who are working on lens, like social graphs, and they have some capital in the project, which means that it uses DeFi in some way. You could use APY to not have the capital sit around and do nothing. So you could actually put it to work. So this is just one of the ideas that you could leverage APY for. And creative strategies are going to get rewarded. For this hackathon, we are sponsoring with a few prizes. Let me show you here. All right, so we have 3 prizes for AP Wine. First is the Wine Connoisseur. This is the first prize, 5K in APW. And the 2 other ones, the runner-up prizes, are 2.5K in APW each. So again, if you are still brainstorming, we would be super happy to help. Some of you have probably already seen our stand, our booth at ETHBogotá. So please, anytime during the weekend, please feel free to come along, chat with us, and we can brainstorm together to make an amazing project. I feel like there are so many ideas possible with different projects, so it's up to you to really leverage as many kind of prizes as you can to get the best out of it. All right, thank you so much for listening to this workshop. Really appreciate seeing you here. Also a note that we are hiring front-end developers, Solidity developers as well. So if you're interested, even at the end of the hackathon, to talk more with us, please reach out. We'd be super happy to chat. Thank you so much for listening today, and good hacking. Any questions so far? We have a few minutes for questions, but again, there's going to be time during the weekend to answer any of your... Yes, please.
It was a little bit late, but what is the difference between PYT and PT? PT is the one used to unstake your ETH.
Yeah, good point.
PYT is the one you can swap for ETH, so you can have your yield on advance.
Yeah, so how AP1 works is you start with your ADI, for example, like very simple interest-bearing asset. Interest-bearing asset means that it generates yield over time. You deposit that on AP1. And the primitive that we came up with is the future yield tokenization. So it splits this interest-bearing token into two tokens. If you deposit $100, your PT is going to be worth exactly $100, not more, not less, all the time. And because this generates yield, all the yield over $100 is going to go not in the PT, but into the FYT. So from the time 0 to the time, 1 month after, all the yield is going to go inside of the FYT.
And for example, I can use the principal token on compound, so I can get a loan.
Exactly. No, please. What I meant to say is you can use Compound to generate yield and then go on AP1 to tokenize that yield. It's very interesting, though, that you mentioned borrowing with PT as collateral. Yeah, well, you could definitely try doing this during the hackathon. This is a very good first idea. Definitely something that we're looking into, but please feel free to try. Awesome. Thank you so much for the question. Any other questions so far? Yes, please. Yep. Yeah, that's a very good point. Maybe I can show the interface. So basically, all right, if you go on AP1, you're going to see all the features that we support. And what you mean is here the LP APY, right? So PT, for example, underlying, and then PT FYT, right? Correct? Oh, this one? The TVL? The market APR. Okay, that's a very good point. Maybe we can take a few minutes to explain this. So the market APR is what you're going to get on AP Wine if you go into either the PT strategy, so buying PT, or into the FYT strategy, so selling your future yield. So let's look at an example. Staked AVE, for example, if you go on AP Wine and you get a fixed rate, you're going to get 8.1%. Okay? This is right now. If you sell your future yield and you get it in advance, you're going to get 7.82%. So essentially, it's fixed rate on top, PT, versus fixed rate plus yield in advance. So it's lower, right? Because it's had some discount. And then here, the LP APY. This is going to be the APY that you can get by providing liquidity on either of those pools. So there are two pools on AP1 for each AMM. There's, on Uniswap you have two tokens, right? On Balancer you have 3 tokens, and on AP1 we also have 3 tokens. So the PT, the underlying, and then the FYT. So for example, PT, DAI, or ETH, or whatever, and FYT. There's 2 pools you can provide to. So if you provide to the first one, which is PT underlying, this is the most stable and riskless pool because you only get exposed to minimal and permanent loss. This is going to give you 0.6% plus 95% in rewards of APW. If you provide to the PT-FYT pool, which is a little bit more risky, but it's also another strategy because you get exposed to the volatility of the yield, you get 6.1% plus this amount in APW. I hope that answers your question. Awesome. Yes, that's an arbitrage opportunity right now. It either means that the liquidity is low enough that there might be arbitrage opportunities right now to take, because like higher volumes can't keep up, or it can mean that we're very close to the period being expired. So like because there's like only a few days left, there's like this arbitrage opportunity also. So if you see anything negative, it can also be a hackathon project, a bot that takes advantage of any arbitrage opportunities on AP Wine. So that's a very good point. So essentially, you would just tokenize and then sell your PT. It means the PT is above 1, so there's arbitrage to be made.
And probably they can go to SushiSwap or other DEX, and I can use my PTs right now and get my ETH back earlier?
Yes, you need to go on the AP1 AMM though. Oh, okay. Yeah, but same concept as SushiSwap or Uniswap or anything you're comfortable with already using. Yeah. Awesome. Thanks for the question. Anyone else? All right. Again, just want to mention, thank you guys so much for coming. We have the booth all weekend. And so please feel free, even if you're still brainstorming ideas or if you're building on top of AP Wine, want to get some feedback and input, feel free to reach out to us, and we would be super happy to help you guys. Awesome. Thank you so much. Happy hacking again.
Does it work? Awesome. Yeah, that's perfect. Hi everyone, I'm Kevin from Boba. Not sure if you have heard about Boba Network yet. It's an optimistic rollup that allows you to make off-chain calls within one single atomic transaction. And that's called hybrid compute, formerly Turing. That's what I'm super grateful today that I'm allowed to present you today. To give a little bit of backstory of why we started with hybrid compute. Basically, we have all seen the craze last year with the play-to-earn games, right? Axie Infinity and all those copycats and comparable play-to-earn games, which unfortunately weren't that sustainable, right? And we don't have a solution for that, unfortunately too. But we at Boba believe that it's time for great games, right? And great games, what have all of them in common? Great UX, right? They have an amazing gameplay. It's not like you need to wait for some things. It's easy, it makes fun, and you don't play games just to earn money, but because it's fun and to maybe even have some additional benefits, like gathering, collecting some NFTs or whatsoever, right? And that's what hybrid compute for, right? And before I get too deep into the technicalities, I want to give you a little bit of backstory. What's the differentiation between hybrid compute, where you can make these off-chain calls, and regular oracles, right? Because that might be the first thing that you think about when I say you can directly call from your smart contract an external API point and do some cool stuff with it, right? Not sure if everyone here ever used Chainlink, UMA, the optimistic oracle that's also here today. All of them have amazing solutions, right? Don't get me wrong. They have their use case. They do incredible work with requesting data in a decentralized, secure manner, right? But when looking at GameFi, do we always need that async, fully decentralized way of collecting data into our smart contract, right? I'm a smart contract developer myself. I love decentralization, right? So why are we talking about centralization now? In the whole blockchain space, we always have that trade-off between scalability, security, decentralization, right? And when we go back one step and think about GameFi, UX is still a great gameplay, still the most important aspect in the whole GameFi space, right? And almost all Web3 games incredibly, unfortunately, fail at this, right? And we need to change that. So in comparison to all these oracles that we have now, as said, different use case where we need to wait several transactions, minutes, hours, or even longer, depending on the sensitivity of the data, there might be the need at some point that you can actually request data on time, right? Within the same transaction. Just think about when you play a game, you earn a nice little skin, like a cool jacket or anything like that. And you would like to personalize that in some kind of way, right? You want that some personal data that you have on your centralized backend, want to have that within your NFT in an autonomous and trustless manner as much as possible, right? So what you can do now, you can have within your smart contract, you can call your API endpoint in a synchronous way, get the data, and directly work with it. And that actually gives you a whole new possibility or opportunities to build some great new applications, right? As said, different use case than oracles. And that's what we're going to do today. So basically, to give you some understanding how that in general works, right? Boba is, as said, a layer 2 solution. So what we basically did, we modified layer 2 GAF. And when you basically call that smart contract function that triggers that API call, then we intercept that RPC call and replace the original call data with the result of the API call and save both of them to layer 1, which is in our case Ethereum. And that enables us to do that in the same transaction. So to give you some understanding, let me get that to the other screen. To give you some understanding before you get shocked away by code, the whole Turing landscape, which is, as said, the old name for hybrid compute, you will see that now and then on some places, because everyone who has ever run a company knows that replacing a name is unfortunately a really difficult task. In general, we have 3 core components, right? Or actually, it's 4. We have your own smart contract that triggers the API call. Makes sense, right? Then we have your backend itself that understands or needs to understand some way that needs to understand what kind of information you're sending from your smart contract to the backend, because it will be or needs to be API encoded. It just can't be plain text or something like that. And the same way, other way around. If you return data from your backend to the smart contract, it also needs to be in an understandable format. And now we're coming to 2 other smart contracts that we might need to know or think about. And that's on one hand, the so-called Turing helper, or hybrid compute helper, as you wish, and the Turing credit. And both of them have a really close interplay. One of them, the Turing helper, is a smart contract that every project needs to deploy themselves. That contract basically is nothing else than your personal, let's say, key to your backend. Let's put it that way. And the Turing credit contract basically keeps track of your Turing helper, your smart contract. But why am I saying this? As with every Oracle, you need to pay for each transaction, right? For each API call, you need to make a small deposit. In our case, it's a prepay. So you need to prepay your, if you basically deploy a project, you need to prepay the amount of Boba tokens that you want to fund in advance, right? So that your users can actually trigger those smart contract functions. So every time you call your smart contract, there will be 0.01 Boba token, which is around a few cents currently deducted from your prepaid balance. And the Turing credit contract is deployed by us, the Boba team, which keeps track of your balance basically. And the Turing helper contract is some kind of authorization, right? So that only your users or the contracts that you want, your custom smart contract can actually call that endpoint. Otherwise, I could just use your endpoint for free, right? And you would pay for it. That's why we have 2 smart contracts here. But enough theory, sorry for that. I want to show you a little bit. What you see here is really a quite minimalistic example that I want to implement with you today. And what it basically does, it calculates the time dilation from based on the special relativity theory by Albert Einstein. Sounds complicated right now. It's just a basic math formula, which would be quite hard to calculate in a smart contract, as you can imagine, right? And that's why I chose that for today. If you want to do that with me, I have prepared a starter repository that I would ask you to clone. Then we could actually do that. Basically, it's on our official organization, and it's called hybrid compute _tutorial. That default branch is already the one that you can use to implement that with me today. And yeah, there's basically everything is already set up, and we will go through every step that it's actually needed to perform your Turing call. To give you a first insights on what we are talking about at all, I want to show you how does such a API call actually look like, right? The most, right, let me look here. That's a more beautiful example. You can see it here. Basically, it's really just a one-liner, right? You can actually call your smart contract by calling a method on the so-called Turing helper that, as said, your project needs to deploy it themselves. But you don't need to change a single line there. It's really just a fully prepared, already ready to deploy smart contract that you can use. You just needed to actually keep track of your balance, right? To get back to the repository, to give you, as said, a little bit of overview, we have said we have a couple of components here, right? We have our own custom smart contract that we will implement today. We have our so-called Turing helper, ready to deploy, nothing to change, basically copy-paste, that actually tracks if your smart contract is allowed to call that endpoint, to actually be charged for that. So it's a whitelisting and some other, error handling stuff and whatever. But as said, you basically just need to know two core functions that will be useful for you. On one hand, you have the so-called Turing random function, which gives you a super strong pseudo-random number directly from layer 2 graph. And we have the so-called Turing TX function, where you can call any endpoint with any call data you want. That's where you can actually do your off-chain calculations or call further APIs, such as Twitter or whatsoever. And yeah, basically, that's the Turing helper. That's our custom contract that we will deploy today. And then you will need your own custom backend, right? That understands the data you're sending to and data that you're returning from. In our case, we just used AWS Lambda function. That's already prepared for us. I still uploaded it here so that you can actually have a look at it and understand it. But basically everything that it does is decode the API encoded data and encodes the result as well. So nothing super complicated or magic here. But as said, that's already deployed. So if you have cloned that for yourself, what you can do now is, as always, if we deploy on testnet, we will need some kind of testnet tokens, right? Otherwise, it's going to be hard to actually deploy anything. We have a nice little faucet for that on our gateway. You can find it if you type on the search bar gateway rinkaby.boba.network. And as you can imagine right now, that's the faucet basically. This faucet itself actually uses hybrid compute itself. What it does is it asks you to copy your so-called boba tag, which is nothing else than the boba prefix with MD5 hash of your public key, and post that on Twitter, just like I did here. If you have that, just need to copy the link and can put it in here. What this does now, if you click on authenticated faucet, it actually requests from the smart contract the Twitter API and checks if you have posted that, and then sends you the boba and Eve. So that's what you would need to follow the workshop today. So if we go back to our own project now, what I did is to actually give everyone here a little bit of a safe haven. If you code that today, then I want you to be sure that it actually works, right? For that very same reason, I wrote a simple test that actually checks if you did it right. So nothing to be done here, but basically what this test does is it returns, it checks the event that I'm emitting in the smart contract, which we need to do, right? Right now it's undefined, undeclared variable. And yeah, then basically it just checks if the value within the event is the one that we are expecting to. And yeah, small hint, not to confuse it too much, but basically, as you might know, Solidity smart contracts don't support floating numbers, and this formula returns actually a really small number. That's why I multiplied on the backend the floating number with 1 trillion, and here I'm just dividing it back to a value that makes sense. So basically, what this would do now, it calculates how many minutes basically your time is stretched if you almost move at the speed of light. Right? We're very close to the speed of light here. That's the velocity parameter. And then we have the proper time, which is the original time that we as a person actually feel like it is. I think everyone here, or most people, have seen the movie Interstellar. Not all of it is science fiction. The part of it where gravity and basically the speed of your aircraft stretches the time is true. So let's get hands-on. Right? I have prepared some setters on top here, which you don't necessarily need, right? As you know, you can provide everything yourself. But basically, every time when we want to use hybrid compute, we need our own custom Turing helper. Right? That's the contract that we need to deploy ourselves. That's the one that we had a look at before, right? The one with the error codes and with the Turing TX function, with the Turing random function, and so on. So that's basically just deployed by us. I'm just assuming that for now. And basically what you need to do is provide that address to the contract so that your custom smart contract knows where to redirect your call data to. The second would be, what's your actual backend, right? What's your actual backend API URL? And that can be anything, as you might guess. In our case, it will be an AWS Lambda instance, which you can use yourself. I already pasted it in the tests. If you look here, it's on top. It's here. That's already live. So basically, that's our Python file that we see here. So to actually make that work now, we now have, or assume that we have, our hybrid compute helper. We assume that we know where the information should actually flow to. And now we actually need to do 3 basic steps, which could be in theory a one-liner, but I want to make it simple. So the first thing we would need to do is encode our parameters that we want to send to our backend in a way that the smart contract is able to handle. So basically, what we need to do is we need to create a bytes value. I'm just calling it right now params. And we basically just encode our 2 parameters that we get from this function. Proper time, those are the 15 minutes that we saw before, and the speed that we are moving at. So that's the first thing. Basically, we encode the data in an understandable format. So the next thing that we need to do is to actually do our synchronous API request. So that works in a quite similar way with the TuringTX method that we saw before. What we get from the API itself is, again, a bytes value. So it's really, it needs to be in a format, again, that the smart contract understands. So basically, we get here our bytes memory again. I'm calling it RESB for now. I know that's not best practice. And now our so-called hybrid compute helper comes into play. And we see now that we have our TuringTX and Turing random function that we can use. The TuringTX function basically, let me see if we see that even here, yeah, requests that we send the URL. That's our HC endpoint in this case, which is just a regular string, and our already encoded parameters, the ones above. That's it, basically. That simple line sends an API request to your backend. No callback, nothing else. Super simple. And the next thing, what should I do with bytes now? No usage for that. I want to have some kind of proper value, right? I want to have a number, I want to have a string, whatsoever. Now it would be great if you know what your backend returns, right? Otherwise you get some random value out of it. In our case, I know that it's an integer value. So what I'm doing now is defining that the first value of my tuple is just a number. And I decode the RESB value that we just got into uint. It's always great to develop on 2 displays. So that should be it, right? And that result that we get now, we just emit the event so that our test can actually read it and check for the accuracy. That would be the whole magic. This, as said, I hope I didn't confuse you too much, right? It's always a little bit difficult to go from 0 to 100, but basically this enables you to do a lot of crazy new things, right? Things that you couldn't do that easily before, but everything is possible right now, right? We have oracles, we can do everything, but we all know, we all went through callback hell in Web 2, and it also can exist in Web3, right? As said, Chainlink, UMA, all oracles are great. They have their use case. This is a different one. So now I'm going to do the most risky part of my presentation. I'm trying to run the tests. Let me see if everything works. So what these tests now do, they basically deploy our Turing helper. Let me show you. They deploy the Turing helper here. As said, that's just our prepared contract from before. Our own smart contract, where we actually provide the Turing helper address and our backend URL. In this case, as said, AWS Lambda instance. And what we need to do now is we need to know, or basically the Turing helper needs to know which smart contract is actually allowed to call my Turing helper, my endpoint, right? For which smart contract I'm willing to pay for, right? Otherwise, as said, I could deploy a smart contract and one of you needs to pay for it, right? Wouldn't be so cool. That's this line, basically a whitelisting to protect your funds. When we're talking about funds, we also need to basically fund the Turing credit contract, which keeps track over your funds by actually knowing your Turing helper contract address. Because your Turing helper triggers that API call finally, and that's why the Turing credit knows from where the call comes from. That's what we do here. We basically just add some Boba tokens to the Turing credit contract. And the rest is just some basic checking if we get the correct address back and so on. So that's basically it. I'm super happy that this works. And I hope you learned something. Maybe you got even some kind of like crazy ideas for the next few days. I don't know. I would love to know them. And yeah, if there are any questions, I'm happy to answer.